Takis, Butterfinger, and Reese's peanut butter cups all hide the same question inside the first bite. How does a corn chip become a rolled fireball, candy turn crisp under chocolate, and peanut butter stay soft inside a perfect ridged cup? In this video, we uncover the iconic steps behind 3 snacks built around a taste people keep coming back for. Takis disappear into a rotating seasoning drum, almost completely plain, but by the time they tumble back into the light, only seconds later, every tightly rolled tortilla has become coated in an intense layer of deep red seasoning that clings to every curve and every edge. Clouds of finely milled chili powder swirl through the drum as thousands of spinning rolls continuously collide, separate, and roll again, building the bold coating that makes the snack instantly recognizable. It looks like the final step, yet none of that seasoning would stay attached if the tortillas had not already passed through an extraordinary sequence of mixing, sheeting, rolling, frying, drying, and cooling. The dramatic color is only possible because every earlier stage has prepared the surface with remarkable precision. The process begins in an entirely different part of the factory, where yellow corn flour arrives from enclosed storage silos through pneumatic conveying systems. Unlike ordinary cornmeal, the flour used for tortilla-based snacks is selected to create a smooth, flexible dough capable of being rolled tightly without cracking. Automated weighing stations measure every ingredient before it enters massive ribbon mixers alongside carefully controlled quantities of water, salt, vegetable oil, and functional ingredients that influence elasticity and strength. Wide rotating paddles fold the ingredients together continuously until every dry particle has absorbed moisture. The loose flour gradually transforms into a dense golden dough with a remarkably consistent texture from one end of the mixer to the other. Instead of sending the dough immediately toward forming equipment, the factory allows it to rest inside enclosed conditioning hoppers, where moisture continues migrating naturally throughout the mixture. Although the dough appears motionless from the outside, hydration continues balancing itself between every particle of corn flour. This short resting period improves flexibility while reducing internal stresses that could otherwise create cracks during rolling. Temperature sensors and automated timing systems carefully monitor every batch because even slight changes in conditioning influence how the dough behaves later on. The conditioned dough now begins one of its most important transformations. Heavy sheeting rollers compress the dense mass into broad, continuous sheets, while each successive roller reduces thickness slightly more than the previous one. Instead of flattening the dough in one aggressive movement, the factory gradually stretches it into an endless ribbon with nearly identical thickness across its entire width. Laser measuring systems positioned above the conveyors monitor every section continuously, allowing computer-controlled adjustments to maintain remarkable consistency. By the end of the sheeting line, what entered as a heavy block of dough has become a smooth, flexible sheet, moving steadily toward high-speed cutting equipment. Rotary cutters descend rhythmically onto the traveling sheet, stamping out long oval sections that will soon become the familiar rolled tortilla shape. Every cut happens in perfect synchronization with conveyor speed, producing identical pieces while leaving very little waste behind. Remaining dough surrounding the cut shapes does not leave the production process. Instead, recovery conveyors transport it back toward controlled blending systems, where it rejoins fresh dough in carefully regulated proportions before returning to the beginning of the sheeting line. Meanwhile, the newly cut pieces continue forward, still completely flat and soft. Now the process reaches one of the defining moments in Takis production. Mechanical rolling systems gently lift one edge of every oval tortilla before guiding it around specially designed forming rods. As the conveyors continue moving, the dough wraps tightly around itself, creating the compact hollow cylinder that distinguishes Takis from flat tortilla chips. The rolling process happens with surprising speed, yet every movement remains carefully controlled to keep the cylinders tight enough to hold their shape without sealing the opening completely. Watching thousands of perfectly rolled tortillas move side by side across the conveyor reveals just how much precision is required before frying can even begin. Freshly rolled tortillas still contain far too much moisture to become crisp. They first pass through a short preheating section where warm air gently begins drying the outer surface while helping stabilize the rolled shape. This brief preparation reduces surface moisture before the snacks encounter hot cooking oil, encouraging more even frying while helping the cylinders retain their structure. Conveyor speed and airflow remain carefully balanced because excessive drying at this point could create surface cracking before the frying stage. The preheated rolls now travel toward the continuous fryer, where shimmering cooking oil stretches across the full width of the production line. Conveyor belts guide every rolled tortilla beneath the oil surface, and the transformation begins immediately. Tiny bubbles erupt from every opening as water trapped inside the dough rapidly converts into steam. That escaping steam leaves behind countless microscopic spaces throughout the tortilla, gradually replacing moisture with crispness. The rolled geometry creates an especially interesting cooking pattern because hot oil reaches both the outside surface and portions of the interior simultaneously, producing an even texture throughout the hollow cylinder. Throughout frying, temperature sensors monitor the cooking oil continuously, while filtration systems remove tiny food particles before they can affect later batches. Conveyor speed determines exactly how long every rolled tortilla remains submerged, ensuring identical cooking from the first piece to the last. As the snacks approach the end of the fryer, their color shifts gradually from pale yellow to a rich golden shade while the structure becomes increasingly rigid. They now possess the familiar crunch associated with Takis, yet they still lack the bold flavor that defines the finished product. Emerging from the fryer, the freshly cooked rolls pass across draining conveyors where gravity begins removing excess surface oil. Gentle vibration encourages remaining oil to leave the hollow centers, while carefully positioned air knives direct streams of air across the moving product. This balancing act removes enough oil to produce the desired texture, while leaving just enough behind to support the seasoning stage waiting ahead. The rolls continue cooling slightly as they move along wide conveyors, preparing for one of the most visually dramatic transformations inside the factory. Elsewhere in the production facility, enormous ribbon blenders have been preparing the seasoning mixture. Fine chili powders, salt, spices, dehydrated vegetable powders, acids, sugars, flavor compounds, and vivid coloring ingredients enter the mixers through automated weighing systems before rotating blades fold the ingredients together repeatedly. Every component disperses evenly throughout the blend until no visible concentration differences remain. Depending on the specific Takis variety being produced, additional spice blends or flavor systems may be introduced, but every formulation must remain exceptionally fine so it coats the rolled tortillas uniformly. Before dry seasoning is applied, precision spray systems deliver an almost invisible mist of vegetable oil across the warm snacks as they enter enormous, rotating flavoring drums. The oil layer is extremely thin, yet performs a crucial role by creating the surface adhesion needed for the powdered seasoning. As the drum turns steadily, every Takis roll climbs partway up the rotating wall before sliding back through the center in a continuous cascade. This tumbling action ensures every surface remains exposed repeatedly throughout the coating process. Now the seasoning begins. Precision feeders positioned above the rotating drum release controlled clouds of crimson powder that drift downward across the moving rolls. Every rotation exposes a different side of each tortilla, while the fine particles settle onto the lightly oiled surface. The hollow cylindrical shape causes the snacks to roll continuously through the seasoning, allowing powder to reach both the outer surface and portions of the inner opening. With every revolution, the pale golden tortilla disappears beneath increasingly intense layers of red seasoning until the familiar appearance finally emerges. The transformation happens in less than a minute, yet the consistency depends on every stage that came before it. Computer-controlled dosing systems constantly compare seasoning flow with product throughput, adjusting feed rates whenever production speed changes. If more tortillas enter the drum, additional seasoning is introduced automatically. If throughput decreases, the dispensers reduce output to maintain the same coating thickness. Sensors also monitor drum rotation speed because excessive tumbling could damage the crisp rolls, while insufficient movement would produce uneven flavor distribution. Butterfinger disappears beneath a flowing curtain of liquid chocolate as long rows of peanut butter centers glide through the enrobing machine, leaving only a thin wave behind them before emerging completely coated in a smooth, glossy shell. For a few seconds, the chocolate surface looks almost like a mirror, reflecting the bright lights hanging above the conveyor. It is one of the most satisfying moments in the factory, but that crisp chocolate shell is only protecting something far more unusual hidden inside. Beneath the coating lies a flaky layered peanut butter center, unlike almost any other candy bar. And creating that brittle interior requires an entirely different manufacturing process built around repeated folding, cooling, stretching, and layering long before the chocolate ever enters the picture. The journey begins inside large stainless steel cooking kettles where granulated sugar, corn syrup, and carefully measured water are combined under continuous agitation. Steam jackets surrounding the kettles gradually raise the temperature, while powerful mixing paddles prevent localized overheating. At first, the ingredients resemble a simple clear syrup flowing freely around the vessel, but as moisture slowly evaporates, the liquid becomes increasingly concentrated. Sensors positioned throughout the cooking system continuously monitor temperature and solids content because the exact concentration determines how the candy behaves during every later stage. The syrup thickens steadily, developing the dense consistency needed to create the signature crisp interior hidden inside every Butterfinger bar. While the sugar syrup reaches its target concentration, roasted peanuts begin following a completely separate production path. Large batches enter industrial grinding equipment fitted with heavy-duty milling plates that gradually reduce the nuts into an exceptionally smooth peanut butter. Unlike coarse peanut butter used in spreads, this version must remain remarkably uniform to blend consistently with the cooked sugar mass. The grinding process generates heat through friction, so cooling systems maintain carefully controlled temperatures throughout milling to preserve the desired texture. Once complete, the peanut butter travels through enclosed pipelines toward blending vessels where it waits for the next stage. Now, two very different ingredients finally meet. The concentrated sugar mass leaves the cooking kettles while still extremely hot and enters blending equipment already receiving measured quantities of peanut butter. Powerful mixers fold the dense ingredients together continuously, transforming the glossy sugar syrup into a rich golden confection. At first, the mixture appears streaked as the peanut butter begins dispersing, but every rotation blends the ingredients more completely until no visible separation remains. The warm candy develops a smooth, creamy consistency that still flows readily through the equipment, yet hidden inside is the foundation for the crisp, flaky texture that makes Butterfinger so distinctive. The blended candy now travels toward cooling tables where its transformation begins accelerating. Rather than allowing the mixture to cool randomly, wide temperature-controlled surfaces remove heat gradually, while mechanical paddles keep the confection moving. As the temperature falls, the candy becomes noticeably firmer without turning completely solid. Timing during this stage is critical because the next operation requires a material that remains flexible enough to fold while being firm enough to hold thin layers without flowing back together. Now comes one of the defining stages of the entire process. The partially cooled candy enters a series of folding machines that repeatedly stretch, flatten, and fold the mass back onto itself. Every pass creates another thin layer while trapping tiny pockets of air between adjoining surfaces. Instead of producing one solid block, the repeated folding gradually builds a delicate laminated structure throughout the candy. This layering process happens again and again, with each fold multiplying the number of internal layers until the center develops the brittle architecture responsible for Butterfinger's unmistakable flaky bite. Watching the machinery perform the same movement repeatedly may appear simple, but every fold quietly contributes to the candy's final texture. The laminated candy continues through additional cooling conveyors, where its growing internal structure stabilizes before further processing. Conditioned air circulates gently across every surface, while conveyor speeds remain carefully synchronized with upstream production. Cooling too quickly could create unwanted fractures before shaping begins, while cooling too slowly would allow the delicate layers to compress together. Every section of the conveyor maintains its own carefully controlled temperature profile, allowing the candy to reach the perfect consistency for forming. Before shaping begins, laser measuring systems verify thickness continuously, while computer-controlled rollers make microscopic adjustments whenever necessary. Maintaining identical dimensions becomes increasingly important because every later cutting and chocolate coating operation depends on the center remaining remarkably uniform. By now, the candy has transformed dramatically from the flowing mixture that first left the blending vessels. It feels firm, yet surprisingly fragile, ready for another important transformation. Large forming rollers gradually compress the layered candy into wide continuous slabs with precisely controlled thickness. The rollers apply enough pressure to create consistent dimensions without destroying the delicate laminated structure hidden inside. As the slabs leave the rollers, automated trimming systems remove uneven edges, while recovery conveyors transport those trimmings back into carefully controlled recycling systems. The perfectly formed slabs continue forward uninterrupted, preparing for one of the fastest sections of the production line. Servo-driven cutting systems descend rhythmically onto the moving slabs, first dividing them into long continuous strips before cross-cutting blades slice the strips into individual bar-sized centers. Every movement remains synchronized with conveyor speed, so the candy never stops moving during production. Thousands of peanut butter centers appear almost instantly, each carrying nearly identical dimensions and weight. Although they already resemble the inside of the finished Butterfinger, another major transformation still lies ahead before they become recognizable candy bars. Freshly cut centers travel through another cooling tunnel where conditioned air further stabilizes the laminated structure. During this stage, the thin internal layers become increasingly crisp while maintaining just enough strength to survive chocolate coating. This cooling process also prepares the centers for one of the most visually dramatic moments inside the factory. Waiting ahead is an uninterrupted river of tempered chocolate flowing continuously across the production line. Meanwhile, chocolate preparation has been underway inside another part of the facility. Large melting tanks gently warm solid chocolate until it becomes completely liquid before pumps transfer it through tempering equipment. Carefully controlled heating and cooling cycles encourage stable cocoa butter crystal formation, creating chocolate capable of developing a glossy finish and clean snap after solidification. Sensors monitor temperature continuously because even slight variations affect how the coating behaves once applied. The cooled peanut butter centers now approach the enrober. Conveyor belts carry them beneath a wide curtain of flowing chocolate that descends continuously from above. Every center disappears beneath the curtain before emerging fully coated moments later. Excess chocolate drains away across vibrating wire belts, while gentle air blowers remove any remaining surplus from the bottom surface. Although the coating appears complete almost instantly, it still remains completely liquid as the bars continue moving toward another critical stage. Immediately after enrobing, the freshly coated bars enter a refrigerated cooling tunnel, stretching across a large section of the production hall. Inside, carefully controlled streams of cool air remove heat gradually from the chocolate without shocking the product. As the temperature falls, the tempered chocolate crystallizes into a smooth, glossy shell surrounding the delicate peanut butter center. By the time the bars leave the tunnel, the coating has hardened completely while preserving the mirror-like finish created during tempering. The cooled bars now pass beneath advanced inspection equipment. High-speed vision systems examine coating coverage, surface smoothness, dimensions, and overall appearance. Sensors search for exposed filling, damaged coatings, irregular shapes, or incomplete chocolate coverage. Any bar falling outside specification leaves the conveyor automatically through high-speed rejection systems positioned beside the line. Every accepted bar continues toward one of the fastest packaging operations in the factory. Large rolls of printed wrapping film unwind continuously into sophisticated flow wrapping machines, where guiding rollers synchronize packaging material with the moving candy bars. Each Butterfinger enters the wrapping section individually as the film folds smoothly around it. Heated sealing jaws create strong longitudinal seams before cross-sealing systems close both ends of every package in one synchronized movement. Integrated cutting blades separate each finished bar from the continuous film while maintaining remarkably high production speeds. Wrapped bars continue directly into coating stations where production information prints onto every package. High-speed cameras verify code quality immediately afterward, ensuring every wrapper remains fully readable before entering retail packaging. The individual bars then gather on accumulation conveyors where automated lane merging systems organize them into precise groupings based on the intended retail format. Some production runs move directly into multi-pack wrapping, while others proceed toward carton loading. Flat paperboard blanks enter automatic cartoning machines where folding mechanisms create fully formed retail boxes. Mechanical loading systems slide the required number of wrapped Butterfinger bars inside before folding arms close every panel. Hot melt adhesive secures the cartons, while compression conveyors maintain square geometry until the adhesive cures completely. Reese's peanut butter cups roll into a refrigerated tunnel with their chocolate shells still completely liquid. Their glossy surfaces reflecting the bright lights overhead as cold air begins transforming that flowing coating into a firm outer layer. It looks like the final chapter of the process, but hidden beneath the soft chocolate is another transformation that has already taken place. The creamy peanut butter filling inside every cup was prepared through an entirely different production line, and only after two independent manufacturing processes finally merged could the familiar candy take shape. By the time the cups leave the cooling tunnel, chocolate and peanut butter will have become one perfectly layered confection, but everything depends on the careful preparation that happened long before the first mold was ever filled. The chocolate begins its journey inside large enclosed melting systems where solid chocolate pieces enter stainless steel vessels fitted with gentle heating jackets. Rather than exposing the chocolate to excessive temperatures, the tanks warm it gradually, while slow-moving agitators keep the liquid circulating continuously. As the chocolate softens, the separate pieces disappear into one smooth, flowing mass with a glossy appearance and remarkably consistent texture. Pumps transfer the liquid through enclosed pipelines toward tempering equipment, but another critical transformation still has to occur before it can coat a single candy. Inside the tempering system, the chocolate passes through a carefully controlled sequence of heating and cooling stages designed to organize the cocoa butter into stable crystal structures. The liquid is warmed, cooled, and then gently reheated again, while sensors monitor temperature constantly. This process determines how the finished shell will look and feel after solidifying. Properly tempered chocolate develops a clean snap, a smooth surface, and an attractive shine, while incorrectly tempered chocolate can appear dull or develop unwanted bloom during storage. Although nothing dramatic seems to happen while the chocolate moves through polished stainless steel pipes, its internal structure is being completely reorganized before it reaches the molding line. While the chocolate follows its own path, roasted peanuts are beginning an entirely separate transformation elsewhere in the factory. Large batches of peanuts enter industrial grinding systems where progressively finer milling equipment reduces them into an exceptionally smooth peanut butter. Heavy grinding plates and precision refining equipment break the peanuts down until their natural oils combine into a creamy, flowing paste with almost no visible particles remaining. Cooling systems remove heat generated during grinding, so the peanut butter maintains the ideal consistency before blending begins. The freshly ground peanut butter enters large stainless steel mixing vessels, where carefully measured quantities of sugar, salt, and other functional ingredients are added through automated weighing systems. Powerful mixing blades fold everything together continuously until the once fluid peanut butter becomes thicker, smoother, and remarkably uniform throughout the vessel. Unlike spreadable peanut butter found in jars, this filling must hold its shape after depositing while remaining soft enough to create the signature texture inside every Reese's peanut butter cup. Every adjustment to mixing time, ingredient ratio, and temperature influences that balance. Once blending is complete, the peanut butter filling moves into holding tanks equipped with slow-turning agitators that keep the mixture completely uniform without introducing unnecessary air. Pumps continuously circulate the filling while maintaining carefully controlled temperatures that allow it to flow smoothly toward the depositing equipment. The chocolate and peanut butter are now both ready, but they still remain on completely separate production lines. The moment they finally meet is one of the most fascinating stages in the entire factory. Rows of paper cup liners travel along conveyors toward precision molding equipment where the first layer of chocolate is deposited. Each paper liner enters a rigid supporting mold that holds its shape throughout production. Depositing nozzles release measured portions of tempered chocolate into every waiting liner with extraordinary accuracy. At first, the chocolate forms only a shallow pool covering the bottom. Immediately afterward, the molds pass through vibration systems that gently shake the liquid, encouraging it to flow evenly across the base while climbing partway up the paper sides. This movement quietly creates the lower shell that will eventually surround the peanut butter center. Before the chocolate has time to harden completely, the molds enter a short, cooling stage where the outer shell begins stabilizing. The chocolate becomes firm enough to support the filling while remaining capable of bonding perfectly with the top layer added later. Temperature control during this stage is remarkably precise because excessive cooling would prevent proper adhesion between the two chocolate layers, while insufficient cooling would allow the filling to sink too deeply into the shell. Now the two production lines finally merge. Precision depositing heads positioned above the partially formed shells release carefully measured portions of peanut butter, filling directly into the center of every cup. Each deposit lands with almost perfect symmetry, leaving a narrow ring of exposed chocolate visible around the edge. The filling remains thick enough to hold its shape immediately after depositing without spreading all the way to the paper liner. Every cup now contains 2 distinct layers, but the familiar sealed appearance still has not been created. Another row of chocolate depositing nozzles waits only a short distance ahead. These nozzles apply the final layer of tempered chocolate directly over the exposed peanut butter, completely covering the filling while joining seamlessly with the lower shell formed earlier. The liquid chocolate spreads gently until it reaches the outer edges of the cup, enclosing the filling completely inside. From above, the candy already resembles the finished product, yet the entire chocolate shell still remains liquid. The freshly assembled cups now enter the long, refrigerated cooling tunnel where the transformation introduced at the beginning of the process finally unfolds. Carefully conditioned cold air circulates around every mold, while conveyor speed determines exactly how long each candy remains inside. As heat gradually leaves the chocolate, stable cocoa butter crystals formed during tempering begin locking together into a rigid structure. The glossy liquid shell slowly becomes firm while preserving its smooth appearance. Hidden beneath that hardening exterior, the peanut butter filling remains soft and creamy, creating the contrast in textures that defines the finished candy. Emerging from the cooling tunnel, the cups continue toward demolding equipment where they separate from their rigid supporting molds, while remaining inside the familiar paper liners. Mechanical lifting systems release every candy gently onto wide conveyors without disturbing the chocolate shell. At this stage, the paper liner still serves an important purpose by protecting the chocolate from direct contact with handling equipment during the remaining production stages. The candies immediately pass beneath advanced optical inspection systems. High-speed cameras examine chocolate coverage, surface smoothness, overall dimensions, paper liner position, and visible defects, while check weighers verify product weight. Every cup receives individual inspection before continuing. Those showing incomplete filling, exposed peanut butter, damaged chocolate, or incorrect weight leave the production stream automatically through high-speed rejection systems, positioned alongside the conveyor. Accepted candies continue uninterrupted toward packaging. Depending on the product format, individual cups may first enter grouping equipment where robotic handling systems arrange them into pairs or larger assortments. Soft mechanical grippers lift each candy carefully by its paper liner before positioning it precisely inside plastic trays or paperboard carriers. Maintaining exact spacing becomes increasingly important because the wrapping machinery ahead depends on every product arriving in the correct orientation. Peanut butter production begins when raw peanuts enter a roaster and their pale centers start changing into the base of a smooth spread. The peanuts arrive as cleaned kernels, but they still need sorting before heat treatment. They move across vibrating screens that remove small fragments, dust, and oversized pieces. Air separators lift away light skins and loose material. Magnets remove tiny metal fragments before the nuts continue. The accepted peanuts feed into a continuous roaster. Inside, hot air moves through the peanut bed while the nuts travel forward on a belt or inside a rotating drum. The heat drives off moisture and develops the roasted texture needed for grinding. The peanuts darken slightly as they roast. Their internal oils become easier to release. The structure becomes more brittle, so the nuts will break cleanly in the grinder instead of smearing unevenly. Time and temperature are controlled closely because roasting affects color, flavor, texture, and final appearance. The hot peanuts exit the roaster and enter a cooling section. Air pulls heat away rapidly. Cooling stops the roasting action and prevents the nuts from continuing to darken after leaving the oven. The peanuts must reach a stable temperature before the next step. After cooling, the peanuts move into blanching. The thin reddish-brown skins are loosened and removed. Blanching equipment may use gentle abrasion, heated surfaces, or air movement to separate the skins from the kernels. The skins break away as the peanuts rub against rollers or belts. Airflow carries the light skins out of the product stream. The blanched peanuts are now pale, clean, and ready for final inspection. Any remaining dark spots, damaged nuts, or off-color kernels can be removed by optical sorting. Cameras examine the moving peanuts and eject unacceptable pieces with short bursts of air. The sorted peanuts move toward grinding. This is where the solid nut becomes paste. The first grinder cracks the peanuts into coarse particles. Rotating plates or toothed surfaces crush the kernels. Oil begins to release from the peanut cells. The dry nut pieces quickly become a thick, rough paste. The coarse paste passes into a second grinder. The particles become smaller and more oil is released. The mixture grows smoother and more fluid. The paste changes from chunky grit into a heavy flowing mass. For smooth peanut butter, the grinding continues until the particle size reaches a fine range. The texture must be creamy but still dense. If particles remain too large, the spread feels gritty. If the grinding is too aggressive, the paste can overheat and change consistency. For crunchy peanut butter, a portion of peanuts follows a separate chopping path. These peanuts are roasted, blanched, and cut into controlled pieces rather than ground completely. Screens separate the chopped nuts by size. Fine powder and oversized pieces are removed. The accepted peanut granules are stored separately until they are folded into the smooth base. The ground peanut paste enters a mixing tank. Salt is added in a measured amount. Sweetener may be added depending on the formula. Stabilizing fat or emulsifying ingredients may also be added to reduce oil separation and improve spreadability. The mixer works slowly but powerfully. Peanut paste is thick, so the agitator must move heavy material without whipping in too much air. The blades fold the ingredients through the paste until every portion has the same salt level, sweetness, and consistency. Stabilizers are important in many commercial peanut butters. Natural peanut oil can separate and rise to the surface during storage. Stabilizing ingredients help hold the oil within the paste structure. The mixture becomes more uniform and less likely to form a liquid layer at the top of the jar. The paste may be heated slightly during mixing to improve flow. Warm peanut butter moves more easily through pipes and fillers. The temperature is controlled because too much heat can affect texture and flavor. For crunchy peanut butter, chopped peanut pieces are added after the smooth base is fully mixed. A gentle blending system folds the granules through the paste. The movement must be strong enough to distribute them evenly, but not so rough that the pieces break down into dust. The peanut butter then passes through a deaeration stage. Grinding and mixing can trap small air bubbles inside the thick paste. In a vacuum chamber, reduced pressure pulls air from the product. Bubbles expand, rise, and collapse. The paste becomes denser and smoother. Deaeration helps the filling process. A paste with trapped air can create inconsistent jar weights and visible pockets. Removing air gives the peanut butter a more solid, continuous appearance when filled. The finished peanut butter moves into a holding tank above the filling line. The tank may be jacketed to maintain temperature. Slow agitation keeps the product uniform without damaging texture. From here, pumps send the spread toward the filler. Jars are prepared on a separate packaging line. Plastic or glass containers arrive empty and are organized by an unscrambler or depalletizer. They move into single-file lanes on a conveyor. Before filling, the jars may pass through an air rinser. Each jar is inverted or positioned under a nozzle. Filtered air removes loose particles from the interior. The jar returns upright and continues toward the filling station. The filler is designed for thick product. Peanut butter does not pour like water. It stretches and holds shape. Piston fillers, rotary positive displacement fillers, or servo-controlled pumps measure each portion and push it through wide nozzles. The nozzle lowers toward the jar opening. Peanut butter enters as a dense ribbon, folding into the bottom and rising steadily. The filling speed must prevent air pockets while keeping the jar rim clean. As the level rises, the nozzle may lift to stay just above the product surface. When the correct weight or volume is reached, the valve closes. A cutoff action stops the thick stream cleanly. Some nozzles use a brief reverse pull to prevent strings of peanut butter from trailing across the rim. Filled jars move to the leveling or settling section. A short vibration or controlled movement can help the surface flatten slightly. The top remains thick and matte with a slow settling texture rather than a liquid surface. The jars then enter the capping area. Caps are fed from bulk hoppers into sorting bowls. The sorter orients each cap and sends it down a chute to the capping heads. Before the cap is applied, some jars receive an inner seal. A foil liner may be positioned over the mouth or built into the cap. When induction sealing is used, the capped jar passes beneath an induction head. Electromagnetic energy heats the foil layer and bonds it to the jar rim. The capper places a cap on each jar and tightens it to a controlled torque. Too little torque can create a weak seal. Too much can damage the cap threads or make the package difficult to open. The machine repeats the same tightening motion across every jar. After sealing, the jars pass through inspection. Check weighers verify the filled amount. Vision systems check cap presence, cap angle, jar shape, fill appearance, and possible product on the rim. Any defective jar is rejected automatically. If product residue appears on the outside, jars may pass through a cleaning station. Wipers or air jets remove smears from the surface. Clean jars move more smoothly through labeling equipment and case packing. Labels are applied next. Round jars pass through wraparound labelers. A pressure-sensitive label peels from a backing web and attaches to the jar side. Rollers spin the jar and press the label smoothly around the curve. Pepsi production is astonishing. The liquid entering the first stage is already sweetened, flavored, colored, acidified, filtered, and blended to finish strength. It is cold enough to hold gas efficiently. The carbonator keeps it under pressure while carbon dioxide enters through diffusers or contact surfaces. The gas breaks into fine bubbles, dissolves into the cola, and gives the drink its sharp, sparkling structure. Inside the sealed vessel, pressure is controlled constantly. If the pressure drops too suddenly, the dissolved gas would escape as foam. If the temperature rises, the liquid would hold less carbon dioxide. The system balances liquid flow, gas pressure, and temperature so every liter leaves with the same carbonation level. The carbonated Pepsi moves through closed stainless steel pipes toward the filler. The line stays pressurized. Bends are smooth. Valves open gradually. Every part of the route is designed to keep the liquid calm because turbulence can knock gas out of solution before the package is sealed. The rotary filler is already moving as the drink arrives. Empty containers enter one by one through star wheels that space them evenly. Each container rises or is lifted into contact with a filling valve. The valve seals around the mouth before the beverage flows. For bottles, the filler first balances pressure inside the empty bottle with the pressure inside the beverage bowl. This prevents the cola from flashing into foam when the valve opens. Once pressure is equalized, Pepsi flows down the filling tube and climbs up the container wall in a dark, glossy column. The fill height is controlled precisely. Too little liquid creates an underfilled package. Too much liquid leaves insufficient headspace and can interfere with closure. When the level reaches the programmed point, the valve closes, and the filled bottle moves immediately to capping. For cans, the same goal is achieved with high-speed fill valves that reduce splashing and foam. The can receives the carbonated cola quickly, but the stream is shaped to keep the surface controlled. The can exits the filler with a small open headspace, ready for seaming. Long before this filling stage, the the water has already been prepared. Incoming water passes through a treatment system. It moves through filters that remove suspended material. Activated carbon reduces unwanted odor and taste. Additional polishing steps stabilize the mineral profile and clarity. The finished treated water becomes the base for both syrup production and final dilution. Part of the treated water enters the syrup room. This area produces the concentrated Pepsi syrup. Sweetener is added first. Depending on the plant and product format, this can be liquid sweetener or dissolved sugar. The sweetener enters a stainless steel tank where an agitator keeps the water moving. When sugar is dissolved, the liquid becomes heavier and more reflective. The mixing system keeps crystals from collecting on the bottom. The syrup is circulated until it is smooth and free of undissolved particles. It then passes through filtration before flavor concentrate is added. The flavor concentrate enters through a sealed dosing line. It is added in a much smaller volume than the sweetener base, but it defines the cola profile. The liquid in the tank darkens as caramel color spreads through the batch. Acids, flavor components, and cola ingredients blend into the sweet base. The agitator turns steadily, not violently. The syrup must become uniform without drawing air into the liquid. Air pockets can interfere with pumps and later carbonation. Once mixed, the syrup has a deep color, strong flavor, and much higher concentration than the final drink. The syrup is held in a dedicated tank. From there, it is pumped to a proportioning system. The proportioner combines syrup with treateds, water at the exact ratio needed for finished Pepsi. Flow meters measure both streams. Automatic valves make small corrections while the system runs. The syrup stream is dark and dense. The treated water stream is clear and light. They meet in a blending chamber and become one continuous cola stream. The color remains deep brown, but the sweetness and acidity now match the finished beverage. At this point, the Pepsi is flat and uncarbonated. The blended cola passes through a chilling unit. Thin stainless steel plates separate the beverage from a cold circulating medium. Heat transfers out rapidly. The liquid temperature drops, preparing it for carbonation. Cold cola foams less, fills more cleanly, and holds dissolved gas more effectively. Some systems remove dissolved air before carbon dioxide is added. In a deaeration unit, the beverage moves under reduced pressure or through a controlled contact system. Air separates from the liquid and is removed. This gives carbon dioxide more room to dissolve and helps keep the final taste consistent. The chilled, deaerated cola then enters the carbonator, where carbon dioxide is absorbed under pressure. From there, the drink moves directly into filling and closure. Bottle production can happen on the same site or before the bottles arrive at the plant. PET bottles often begin as preforms. A preform is a small, thick plastic tube with a finished neck and threads. Only the body remains unformed. Preforms enter a heating tunnel. Infrared lamps warm the plastic body, while each preform rotates. The heat must penetrate evenly. The neck finish stays cooler because it already has its final shape and must not distort. The heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, elongating the softened plastic. Then, compressed air expands it outward until it presses against the mold walls. The bottle shape appears in a fraction of a second. The base forms pressure-resistant feet. The label panel forms along the sidewall. The shoulders and body cool against the mold surface. The mold opens, and the finished empty bottle exits by the neck ring. The bottles travel on air conveyors. They are so light that directed air can push them forward, while rails support their necks. The bottles move toward rinsing, filling, capping, labeling, and packing without being squeezed by heavy belts. Aluminum cans arrive open at the top. They are already shaped and usually already printed. The can body is thin, light, and designed to receive an aluminum end after filling. Before filling, cans pass through rinsing equipment. They invert, receive filtered air or water, drain, and return upright. Glass bottles move through inspection before filling. Light and camera systems check the mouth, base, sidewall, and interior. Any bottle with chips, cracks, contamination, or shape defects is removed before reaching the filler. After carbonated Pepsi is filled, closure happens immediately. Plastic bottles pass under rotating capping heads. Caps feed from a hopper into a sorting system that turns them into the correct orientation. Each cap drops onto a bottle neck. The capping head tightens it to a controlled torque. The tamper band locks below the neck ring. Cans enter a seamer. An aluminum lid is placed onto the filled can. The can spins while seaming rolls fold the lid curl and can flange together. The metal folds into a tight double seam. This seam traps pressure without adhesive. Glass bottles receive crown caps or other closures, depending on the format. A crown cap is placed over the mouth and pressed downward. The skirt crimps under the glass bead, forming a gas-tight seal. The sealed containers move through inspection. Fill level sensors check the liquid height. Cameras examine caps, seams, crowns, tamper bands, dents, label panels, and container alignment. A defective bottle or can is pushed off the conveyor automatically. Bottles then continue to labeling. If roll-fed labels are used, printed film unwinds from a large roll. Registration sensors read timing marks. A cutter separates each label. Adhesive attaches one edge to the bottle, and the bottle spins as the label wraps around its body. The trailing edge receives adhesive and presses flat against the first edge. Rollers smooth the film so the label sits tight without wrinkles. The blue Pepsi branding is applied as part of this printed label or already present on printed can bodies. Kit Kat is assembled from a dry, crisp wafer core that is first strengthened and sealed by contact with a warm, fat-based filling, then coated in chocolate, then cooled so the wafer stays crunchy and the bar snaps cleanly on the finger lines. The wafer stream begins as a thin batter system that must bake into sheets with low moisture and uniform thickness. Flour is sieved to remove lumps and to stabilize hydration. Sugar and salt are weighed precisely because they affect browning and sheet brittleness. Water is tempered so batter viscosity stays consistent at the depositor. A small fat or emulsifier addition is used to control plate release and sheet texture. The batter is mixed only until smooth because excessive mixing increases gluten development and makes sheets tough and less crisp. Batter viscosity is one of the main controls because it determines how evenly the batter spreads on wafer plates. The batter is held in a feed tank with gentle agitation to prevent settling of flour fines. From there, it is pumped to wafer irons. Each iron is a pair of heated plates that close, bake, and open in a cycle. A metered dose of batter is deposited onto the plate and spreads under closing pressure. Heat drives rapid water evaporation and sets the starch matrix into a porous, brittle sheet. Bake time is tuned so the sheet dries to low moisture without scorching, because scorch creates bitter notes and weak zones. When the plates open, the wafer sheet is released and moved to cooling. Cooling stabilizes crispness and prevents warping. The sheet is then cut into finger-sized leaves. Cutting uses sharp rotary blades to avoid cracking edges. At this stage, the wafer leaves are extremely brittle and must be handled with low-impact conveyors and minimal drop heights to prevent breakage before lamination. Lamination creates the multi-layer wafer block that defines the bar bite. A thin layer of wafer creme is applied between leaves as an adhesive and moisture barrier. This creme is not the outer chocolate, but a fat-based filling designed to soak slightly into wafer pores and then set. The creme is prepared by blending sugar, cocoa components, milk powders, and fat into a smooth paste with controlled viscosity. Particle size is refined so it spreads evenly and does not feel gritty. The crème is held warm enough to flow, but not so warm that it becomes runny and floods the wafer. Assembly stacks alternating wafer leaves and cream layers. A depositor spreads cream onto a wafer leaf in a uniform film. Another leaf is placed on top, and the stack repeats until the target number of layers is reached. Alignment matters because misaligned leaves create uneven edges and weak points at the snap lines. Light compression follows stacking to ensure contact and eliminate air gaps. Compression must be controlled because excessive force crushes wafer cells and reduces crispness. After stacking, the wafer block enters a setting tunnel. This tunnel cools the block so the creme fat network crystallizes and locks the layers together. The block must become rigid enough for cutting, but not so cold that wafer becomes overly brittle and shatters. The setting profile is staged so the outer surfaces firm first and then the core equalizes. Once set, the block is cut into sticks and then into the familiar finger format. A longitudinal cutter slices the block into wide slabs. A second cutter defines the number of fingers per bar by cutting grooves or separating lanes. A cross cutter then creates bar lengths. Knife sharpness and speed are tuned to avoid crushing the wafer. Ultrasonic knives can be used in some lines to reduce drag through the cream layers and keep edges sharp. The cut wafer fingers are then routed into an enrobing sequence that is designed to seal the wafer from humidity. Chocolate or compound coating is prepared in a separate system where flow behavior must remain constant. The coating is melted and filtered. If real chocolate is used, it is tempered to create stable cocoa butter crystals so it sets with gloss and snap. If a compound coating is used, it is temperature controlled for viscosity and set rate. In either case, viscosity control is critical because it determines coating thickness and whether grooves between fingers fill correctly. Before the main enrobe, many lines apply an undercoat or pre-coat that improves sealing. A thin coat can be applied to the bottom first to reduce moisture migration from the environment into the wafer. The bars then pass through a curtain that coats the top and sides. Excess drains through a wire belt. Air knives remove excess and shape the surface. Air knife settings are tuned to avoid stripping too much coating from corners because exposed wafer edges absorb moisture quickly and lose crispness. If the bar is intended to have fully defined finger lines, the coating flow must not bridge the grooves excessively. Groove definition is managed by coating viscosity, curtain temperature, and belt speed. Too thin a coating leaves exposed edges. Too thick a coating floods grooves and reduces snap separation. The process targets a thickness that seals the wafer while still preserving the break lines. After coating, the bars enter a cooling tunnel. Cooling is staged to set the surface quickly so it does not slump, then to crystallize the full thickness without stress. Stable crystallization prevents bloom and keeps the surface firm for wrapping. Tunnel humidity is controlled to prevent condensation because moisture on the surface can cause haze and can also migrate into wafer through microcracks before the coating fully sets. During cooling, the wafer core is also protected from moisture changes. The internal crème acts as a barrier and binds wafer layers, but the wafer will still soften if the coating does not seal fully. The combination of internal crème saturation and external coating seal is what maintains the distinctive, crisp bite. A properly set bar has a rigid, layered core that fractures sharply and a coating that breaks cleanly rather than smearing. Inspection follows cooling. Vision systems check coating coverage, groove definition, and edge exposure. Weight checks confirm stick length and coating mass. Bars with broken fingers or exposed wafer are rejected because they will soften faster and package poorly. Rework handling separates wafer material from coating material because wafer pieces cannot be remelted like coating. Wrapping is designed to maintain a low moisture environment. Bars are fed into flow wrappers that form film around each unit and seal it. Seal integrity matters because moisture ingress softens wafer and destroys snap. Film tension is controlled so it does not scuff the coating or snap fingers. Print registration keeps graphics aligned with the bar orientation. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons. Collation systems handle bars with minimal impact to avoid cracking finger edges. Cartons add protection against compression that would fracture wafers. Cases are packed and palletized. Storage temperature stability keeps coating crystals stable and reduces the risk of bloom and softening. Corny-style cereal bars are manufactured by first engineering a binder that will set at room temperature, then using that binder to lock cereals and inclusions into a compressed slab, then cutting, coating, and wrapping fast enough to preserve crunch and prevent stickiness. The process starts with the binder kettle because everything downstream depends on how that syrup flows, how fast it sets, and how much moisture it brings into the cereal phase. Sugar and glucose syrup are metered into heated tanks and pumped to a cooker. Water is added in controlled quantity because it affects dissolution and final viscosity. If fat is part of the recipe, it is melted separately and held at a stable temperature so it can be injected precisely. If the bar includes honey or malt extracts, those streams are heated just enough to pump without degrading aroma. Cooking raises solids and defines the set behavior. The syrup is heated to dissolve sugars fully and drive off water to a target concentration. Concentration is monitored by temperature and by inline density because the binder must land in a narrow window. Too wet and the finished bar becomes sticky and soft, and it can weep into the wrapper. Too dry and the binder becomes glassy and the bar turns hard and prone to fracture. Residence time is controlled to prevent over-browning because browning changes flavor and also increases viscosity unpredictably. Once the syrup reaches endpoint, it is cooled slightly to a mixing temperature where it will coat dry ingredients without scorching them. This is the moment when flavors and sensitive components are added. Vanilla and fruit aromas are injected late to preserve volatiles. Acid additions are kept minimal and are dosed as solutions when used, because acidity changes inversion rate and can shift stickiness over time. Emulsifiers can be added to keep fat dispersed in the binder and to improve wetting of cereal surfaces. Dry ingredients are prepared in parallel, and their particle size distribution is treated as a structural parameter. Rolled oats are screened to remove fines that would increase dust and create dense patches. Crisped rice or wheat crisps are screened to remove broken fragments because fragments fill voids and reduce crunch. Nuts and seeds are sized to a narrow band, so they distribute evenly and do not punch through the slab. Dried fruit pieces are conditioned to avoid hard clumps because clumps create weak bonding zones and tear during cutting. Chocolate chips or compound drops are stored cool, so they hold shape and do not smear during mixing. Dry blending begins by assembling cereals and inclusions in a low-shear mixer. The mixer is designed to distribute without crushing crisps. Mixing time is short because every extra minute creates more fines by abrasion. The blend is staged in a feed hopper that meters a consistent mass flow into the wet mixing step. Consistent flow is important because binder dosing is tied to dry mass rate. Wet mixing is where the binder and dry blend are joined. The hot binder enters through a manifold that spreads it across the mixer width rather than dumping it in one spot. Paddles fold the dry blend through the binder so every particle is coated. This stage must be fast because the binder is cooling and thickening continuously. If mixing is too slow, the binder sets in patches and leaves dry pockets. If mixing is too aggressive, crisper components break and the bar loses its light texture. Temperature control is the main stabilizer during wet mixing. Binder must be warm enough to flow and coat. It must not be so hot that it softens chocolate drops or makes fruit pieces smear. The dry blend must not be cold enough to shock the binder and cause premature thickening. Many lines temper the dry blend slightly so the combined mass stays within a workable temperature range for forming. Once the mass is uniform, it is delivered immediately to a forming line. Forming begins with depositing the sticky mass onto a moving belt between side rails that define width. A spreader distributes the mass across the belt and a pre-compression roller evens thickness. The mass then passes under a main compression station. Compression is the defining mechanical step for a cereal bar. It determines density, bite, and cut quality. Compression is controlled by roller gap and pressure. A tighter gap yields a denser bar that holds together strongly and cuts with clean edges. A looser gap yields a lighter bar with more visible cereal structure, but can crumble. Compression must also avoid crushing cereal completely. Crushing generates fines that absorb binder and create hard zones. The line tunes compression so the binder bridges particles, while the cereal retains its internal porosity. After compression, the slab enters a setting tunnel or cooling zone. This zone brings the binder through its set transition. If the binder is sugar heavy, it will transition toward a glassy state as it cools, and water activity stabilizes. If the binder includes fats, it will also set as fats crystallize. The tunnel profile is staged so the slab firms gradually. Rapid cooling can create a hard skin while the interior is still warm and mobile, which leads to warp and internal separation. Setting is also where moisture management is locked in. If the binder retains too much moisture, it will migrate into cereal and soften it over time. If it is too dry, it will continue to pull moisture from fruit inclusions and make them tough. The process targets a moisture equilibrium that keeps cereal crisp and fruit pliable. This is achieved by binder solids, fruit conditioning, and tunnel conditions. Cutting follows once the slab reaches a cuttable firmness. Cutting is usually two-stage. A longitudinal cutter trims edges and splits the slab into lanes. A cross cutter then makes bar lengths. Knife selection is important because the slab contains hard inclusions. Dull knives tear the slab and pull cereal out, creating ragged ends. Sharp guillotine blades or rotary knives slice cleanly. Ultrasonic blades can be used to reduce drag through sticky binder and to keep inclusions from catching. Trim is handled carefully because cereal bar trim can be reintroduced only within limits. Trim contains more fines and has different binder distribution. Too much trim increases density and reduces crunch. Rework ratios are therefore controlled so the product remains consistent. After cutting, the bars can be coated or decorated. If the format includes a chocolate base, a tempered or controlled viscosity coating is applied to the bottom. Bars pass over a coating roller that lays down a uniform film. Excess is stripped to a target thickness. A cooling tunnel sets the coating so it does not smear in wrapping. If a drizzle is applied, nozzles deposit lines across the top, while the base is still tacky enough to bond. Nut or crisp toppings can be added during this tack window. Some products include a wafer layer or a milk compound layer. In those cases, the forming line adds that layer either before compression or after cutting. The same principle applies. The additional layer must not introduce moisture that would soften cereal. Adhesion must be strong enough to survive wrapping without delamination. Before packaging, bars pass through final stabilization. This step equalizes temperature so condensation does not occur inside wrappers. It also allows coatings to reach full set and resist scuffing. Bars are then inspected for weight, length, and coating coverage. Broken bars and off-size bars are rejected because they create crumbs and contaminate seals. Packaging is designed around moisture barrier performance because cereal bars lose crunch quickly if they absorb humidity. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are tuned so seals are tight without heating the bar enough to soften binder or melt coatings. Film tension is controlled because excessive tension can crack coatings or deform the bar edges. Coating is applied for traceability. If bars are packed in multi-packs, individually wrapped units are collated and then overwrapped or cartoned. Cartons add crush protection and reduce bending damage. Case packing stacks. Cartons in patterns that limit compression. Storage conditions are controlled so bars do not experience temperature swings that can cause fat bloom on coatings or moisture migration inside the bar. Mars bar manufacture is a timing problem disguised as a candy problem because 3 materials with very different behavior must arrive at the cutter with the same firmness and then accept a chocolate coat without distortion. The sequence is easiest to understand from the point where the finished bars enter the chocolate curtain. At that moment, the centers must be dry to the touch, straight and dimensionally stable. If they are even slightly warm or soft, the curtain and air knives will round edges and create thin spots. The plant therefore builds the center as a slab, locks its structure by staged cooling, and only then exposes it to chocolate. Chocolate for enrobing is prepared first in process terms because the enrober is sensitive to viscosity drift. Chocolate is melted, filtered, and moved into a tempering loop. Tempering establishes a seed crystal population, so the coating sets fast with gloss and stable snap. Working temperature is held tightly because small shifts change curtain thickness and final coat weight. The chocolate recirculates through the enrober and is filtered to keep crumbs from building up and roughening the surface. While chocolate is being held ready, the bar center is built upstream as 2 layers. The lower layer is an aerated nougat and the upper layer is a caramel sheet. These layers are not cooked together because they need different concentration endpoints and different set behavior. Nougat begins with a syrup that defines solids and elasticity. Sugar and glucose syrup are metered and cooked to a specific concentration. The cooker is run to an endpoint that supports a light chew once the mass is aerated. Too high a moisture content produces a soft slab that cannot be cut cleanly. Too low a moisture content produces a tight nougat that loses its light character. The cooked syrup is cooled slightly, so it can be combined with a foam phase without damaging it. The foam phase is produced separately as a protein solution that is aerated under controlled shear. Airflow rate and back pressure are used to fix bubble size distribution. Density is monitored continuously because it becomes the direct knob for bar weight and bite. Fine bubbles are preferred because they resist coalescence and create a uniform interior. Syrup and foam meet in a continuous folding mixer. Folding distributes syrup through the foam while preserving bubble structure. Heat from the syrup strengthens bubble walls and helps lock the microcell network. Fat is injected as a thin stream to soften texture and reduce stickiness. If the nougat is chocolate flavored, cocoa components are introduced in a way that avoids sudden viscosity jumps, often as a pre-dispersed stream rather than dry powder dumped into the foam. The aerated nougat is then deposited as a continuous slab onto a moving belt. A depositor spreads it to width and leveling rollers set thickness. Thickness is controlled tightly because it defines the core height and influences cooling time. Immediately after deposition, the slab enters a cooling tunnel with staged zones. Early zones firm the surface so it can support caramel later. Later zones reduce internal temperature gradually so the slab does not form a brittle skin over a soft interior. Caramel is produced in parallel as an elastic, high solids mass. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach a solids endpoint that yields chew rather than glass. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it can be deposited as a sheet without running. It is held in jacketed tanks with gentle agitation to prevent a surface skin and keep temperature uniform at the depositor. Layering occurs when the nougat slab arrives at the caramel station at the correct firmness. Caramel is applied as a continuous layer using a slot depositor. A smoothing bar spreads the caramel and fixes thickness. The temperature relationship between nougat and caramel is critical. Nougat must not be warm enough to compress under the caramel head. Caramel must not be hot enough to melt the nougat surface. The interface must bond strongly because cutting will pull on it. After caramel deposition, the combined slab is conditioned again. Cooling at this stage is aimed at making the caramel cut stable. If caramel is too warm, it smears and sticks to blades. If too cold, it can crack, especially at the edges. Cooling is staged to avoid differential contraction between nougat and caramel that would create curl. Once the slab reaches the cutting firmness window, it moves into trimming and portioning. Edge trim removes uneven slab edges and creates a uniform width for lane cutting. Trims are handled as rework in controlled ratios because rework carries different temperature history and can change texture if used too heavily. Rotary knives cut the slab into long lanes. A cross cutter then slices lanes into bar lengths. Cutter timing is synchronized to belt speed, so each bar has consistent mass. Knife surfaces are managed to prevent caramel buildup that would tear edges. The cut centers are then separated and aligned for enrobing. Transfer sections are designed with minimal drop height because impacts can dent nougat and shear caramel. Spacing is controlled so bars do not bridge in the chocolate curtain. Many lines apply a brief pre-chill here to firm surfaces and reduce deformation under the curtain. Pre-chill is balanced, so it does not create condensation when the bars enter warmer chocolate zones. Enrobing coats each center with chocolate on top, sides, and bottom. A top curtain covers the bar, and a bottoming system lays a base layer beneath it. Excess chocolate drains through the wire belt. Air knives shape the coating and control the foot. Air knife pressure is tuned so it removes excess without exposing corners, especially where caramel edges can create sharp transitions. If a surface pattern is applied, it is added immediately after the curtain while the coating is still tacky. A stringer deposits thin lines, and then the bars enter the cooling tunnel. Cooling after enrobing is staged to set the chocolate without stress and without bloom. The first zone sets the surface quickly so the coating does not slump and so the bars can be handled. Subsequent zones cool more gradually to promote stable crystal growth. Tunnel humidity is controlled to prevent condensation that would dull the surface. Bars exit at a temperature suitable for wrapping with coating hard enough to resist scuffing. Inspection occurs after cooling. Vision checks look for exposed edges, thin spots, and misshapes. Weight checks verify that cutting and coating remain stable. Rejects are diverted. Chocolate rework is remelted and returned upstream through the tempering loop. Nougat and caramel rework is handled separately because aeration and moisture history affect its behavior. Wrapping begins when the bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is managed so it does not scuff the coating. Coating is applied. Wrapped bars are collated into multi-packs or cartons and case packed. Whipped cream production begins with liquid cream being standardized to the exact fat level needed for stable whipping. The cream arrives cold through stainless steel lines. It is not yet foam. It is a dense dairy liquid with fat droplets suspended in water, milk proteins, lactose, and minerals. Before it can become whipped cream, the fat level must be adjusted, the mixture must be blended with stabilizing ingredients, and the product must be treated, chilled, aerated, or packed for whipping later. In a dairy plant, raw milk is first separated into skim milk and cream. The milk enters a centrifugal separator, spinning at high speed. The heavier skim phase moves outward, while the lighter fat-rich cream collects closer to the center. The separator discharges both streams continuously. The cream stream is measured for fat content. If it is too rich, a controlled amount of skim milk can be blended back in. If it is too lean, more concentrated cream is added. This standardization creates a cream base with the correct fat percentage for the product being made. Whipping cream needs enough fat to trap air and form a stable foam. The fat droplets partially connect during whipping, building a network around air bubbles. If the fat is too low, the foam collapses quickly. If the fat is too high, the cream can become overly thick or churn toward butter. The standardized cream enters a blending tank. The tank is jacketed for temperature control and fitted with a slow agitator. Sugar may be added for sweetened whipped cream. Stabilizers or emulsifiers may be added in small measured quantities to help the foam hold shape. The dry ingredients are not dumped into still cream. They are drawn into a moving liquid stream. A powder induction system can pull sugar or stabilizers into the cream and disperse them rapidly. This prevents clumps from forming on the surface. The cream remains cold during blending. The agitator turns slowly enough to avoid accidental whipping. At this stage, the goal is uniform liquid, not foam. Every ingredient must dissolve or disperse without trapping large air pockets. The blended cream passes through filtration. Fine screens remove undissolved particles and protect downstream valves, nozzles, and filling equipment. The liquid then moves toward heat treatment. Pasteurization is performed in a closed heat exchanger. The cream travels through narrow stainless steel channels, while hot water or steam-heated fluid flows on the opposite side of thin plates. Heat transfers quickly into the cream. The mixture reaches the required treatment temperature while remaining enclosed in the system. The heated cream may pass through a holding tube for a controlled time. This ensures the entire stream receives the intended heat treatment. The flow rate and tube length determine the holding time. After heating, the cream immediately enters a cooling section. Chilled fluid pulls heat away through the stainless steel plates. The cream temperature drops rapidly, preserving the dairy structure and preparing it for aging. Homogenization may be controlled differently depending on the whipped cream type. Some cream products are lightly homogenized or not homogenized in the same way as milk because large enough fat droplets help whipping. If homogenization is used, pressure settings are chosen carefully so the cream remains capable of forming stable foam. The cooled cream enters aging tanks. These tanks hold the cream cold while the fat crystallizes into the right structure for whipping. Slow agitation keeps the ingredients evenly distributed without introducing too much air. The cream becomes slightly thicker as it rests. Aging is important because cold fat behaves differently from warm fat. Properly crystallized fat droplets can partially join during whipping and support the foam. Without enough cold aging, the cream may whip poorly or lose volume quickly. From this point, production can follow two main factory routes. One route produces ready whipped cream in tubs. The other produces aerosol whipped cream in pressurized cans. Both begin with the same controlled liquid cream base, but they handle air and packaging differently. For ready whipped cream, the aged cream is pumped into a continuous whipping machine. The machine introduces filtered air, or gas, while mechanical beaters shear the cream. Rotating elements break the gas into tiny bubbles and spread them through the liquid. The cream changes rapidly. It becomes lighter in color, thicker, and more voluminous. The fat droplets partially connect around the bubbles, forming a foam network. The mixture no longer flows like liquid cream. It moves as a soft, structured foam. The whipping machine controls overrun, which is the amount of air incorporated into the cream. Too little air produces a heavy product. Too much air creates weak foam that collapses. The machine balances feed rate, beater speed, temperature, and gas flow. The whipped cream exits through a short pipe toward the filler. Long pipe runs are avoided because excessive pumping can damage the foam. The product is soft and delicate, so every transfer must preserve its structure. Empty tubs or cups feed into the filling line. They are separated from nested stacks and placed into pockets on a conveyor. Each container arrives beneath a filling nozzle. The nozzle deposits whipped cream into the container with controlled movement. The product enters as a thick spiral or mound. The foam must fill the container without large voids, but it must not be crushed by high pressure. After filling, a lidding machine places a lid onto each tub. The lid is pressed into place or heat sealed depending on the package. The container now protects the whipped foam from mechanical damage and air exposure. The filled tubs move through check weighing and inspection. A check weigher verifies that each tub contains the correct amount. Cameras check lid position, container shape, and seal condition. Rejected tubs are removed automatically. For aerosol whipped cream, the process is different after aging. The cold liquid cream base is filled into metal cans instead of being whipped before packaging. Empty aerosol cans arrive open at the top and move through cleaning and positioning equipment. The cans are held upright in pockets or star wheels. A liquid filler doses a precise amount of cream into each can. The cream remains mostly liquid at this stage. It has the correct fat, sweetness, stabilizer system, and temperature, but it will foam only when dispensed later through the valve. After the cream dose enters, the can receives a valve assembly. The valve is positioned over the opening. A crimping head presses the valve cup onto the can and mechanically seals it around the rim. This creates a pressure-tight closure. A propellant gas, commonly nitrous oxide for whipped cream systems, is then added through the valve or during the filling sequence. The gas dissolves partly into the cream under pressure. The can is designed to hold this pressure safely and release the product as foam when the valve is opened. The sealed can may pass through shaking or mixing equipment, so the gas and cream distribute evenly. The can remains cold to maintain product quality and pressure behavior. Each aerosol can then move through leak testing. Equipment checks whether the crimp and valve are sealed correctly. A leaking can is rejected. Weight checks confirm that the proper amount of cream and gas is present. The can receives a plastic actuator and cap. The actuator fits over the valve stem and controls dispensing. The cap protects the actuator during handling. Machines place these components at high speed while cans continue moving along the conveyor. Labels may be applied if the cans are not already printed. In a labeled can line, pressure-sensitive labels peel from a backing web and wrap around the cylindrical can. Rollers press them flat. Printed cans bypass this stage and move directly to coding. Coding equipment marks each package with production information. Inkjet printers apply small characters to the tub, lid, can base, or label. The mark is checked by vision systems as the package passes. Fanta, grape syrup, is much stronger than the drink in the bottle. It carries sweetener, acid, grape flavor, color, and stabilizing ingredients in concentrated form. As it enters the blending chamber, flow meters measure every movement. The treated water line moves beside it. Control valves adjust both streams, so the finished beverage holds the same ratio from the first container to the last. Inside the blender, the purple syrup thins instantly. The liquid changes from dense concentrate into bright grape soda base. Its color remains strong, but the texture becomes lighter. The blend is not sparkling yet. It is flat, chilled, and ready for carbonation. Before the syrup reaches this point, it is built in the syrup room. Treated water is pumped into a stainless steel tank. The tank has a polished interior, a bottom outlet, and an agitator that turns at a controlled speed. Sweetener enters first. Granulated sugar may be dissolved into the water, or liquid sweetener may be metered directly into the tank. If sugar is used, the crystals fall into the moving water and disappear gradually. The liquid becomes heavier and clearer as the crystals dissolve. A recirculation pump can pull syrup from the bottom and return it near the top, helping the batch become uniform without leaving dense sweet spots inside the vessel. The sweetened base passes through fine filtration. This catches undissolved material before flavoring and color are added. A clean syrup is easier to pump, easier to meter, and less likely to disturb the filling system later. The grape flavor concentrate enters through a closed dosing line. It is not added by volume guesswork. It is pumped in at a measured rate. The agitator pulls the flavor into the sweet base, and the tank slowly changes character as the grape profile spreads through the syrup. The purple color system is added in the same controlled way. A small amount changes the entire tank. Dark ribbons appear briefly around the inlet before the mixer folds them into the batch. The syrup shifts into a uniform purple tone with no streaks or pale zones. Acid ingredients are dosed into the syrup to sharpen the fruit profile and balance the sweetness. They dissolve into the moving liquid and change the sensory structure of the drink, but the process remains mechanical. Tank, pump, meter, agitator, sample point, and transfer line. The finished Fanta grape syrup rests in a holding vessel. Slow agitation keeps it consistent. Temperature is controlled, so viscosity stays predictable. A pump then sends it toward the proportioning skid, where it will be diluted into finished beverage. The clear water used for dilution has its own route through the plant. Incoming water passes through particulate filtration first. This removes suspended solids that could affect clarity or damage equipment. It then moves through activated carbon, where unwanted taste and odor compounds are reduced. Additional polishing stages may adjust the mineral balance and remove fine impurities. The treated water must be consistent because it forms most of the finished drink. Even a small change in water profile can affect flavor, carbonation behavior, and appearance. After treatment, the water flows into storage tanks. These tanks keep the water ready for syrup making and final blending. Level sensors monitor the supply. Pumps draw from the tanks as the production line demands more volume. From the proportioning skid, the flat Fanta grape beverage moves toward chilling. A plate heat exchanger lowers the temperature quickly. The liquid flows between thin stainless steel plates, while a cold medium flows on the opposite side. Heat transfers through the metal, and the drink leaves colder than it entered. Cold soda accepts carbon dioxide more efficiently than warm soda. It also foams less during filling. This matters because Fanta grape must hold carbonation while moving through pipes, valves, and containers at high speed. The chilled liquid may pass through a deaeration step. In this unit, unwanted dissolved air is pulled from the beverage. Reduced pressure or controlled gas contact helps tiny air bubbles leave the liquid. Removing air makes carbonation more precise and helps the grape drink retain a cleaner sparkle. The flat, chilled beverage enters the carbonator. Carbon dioxide flows in under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the liquid. The drink changes from still purple, soda base into carbonated Fanta grape. From this point, the beverage stays inside closed, pressurized stainless steel pipework. Sudden pressure loss would release foam, so the route to the filler is smooth, short, and carefully controlled. The purple liquid moves forward without open tanks or splashing. Containers are prepared at the same time. PET bottles often begin as preforms. A preform is a thick plastic tube with the neck already finished. Threads and the sealing surface are complete, but the body is still small and heavy. The preforms enter a heating oven and rotate as infrared lamps warm the plastic. Once heated, each preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, while compressed air expands the softened plastic outward. The bottle body forms against the cold mold walls. The base, shoulders, label panel, and sidewalls appear in one fast expansion. The mold opens, and the empty bottle exits by its neck ring. Air conveyors move it forward. Because the bottle is light before filling, it can be carried by its neck while air jets push it along the rails. Cans follow a different path. Empty aluminum cans arrive already shaped and usually already printed. They are open at the top. Before filling, they pass through a rinser that inverts them, blows filtered air inside, and returns them upright. Glass bottles move through inspection before filling. Cameras and light beams check the mouth, base, sidewall, and interior. Any damaged or contaminated bottle is rejected before it reaches the drink. The carbonated Fanta grape enters the rotary filler. The filler contains many valves arranged around a circular bowl. Bottles or cans move into position through star wheels, each one timed to match a filling valve. For plastic bottles, the container seals against the valve. Pressure equalizes before liquid enters. This prevents the soda from foaming violently. Once balanced, the valve opens and purple carbonated soda flows into the bottle. Fine bubbles rise through the liquid as the level climbs. The valve closes at the programmed fill height. The headspace above the liquid is kept within a set range. The bottle leaves the filler and moves immediately to capping. Caps are fed from a hopper into an orienting bowl. Each cap turns into the correct position and travels down a chute toward the capping heads. The head places the cap onto the bottle and tightens it to a controlled torque. The tamper band locks below the neck ring. For cans, the filled container moves into a seamer. An aluminum lid is placed over the open top. The can and lid rotate together while seaming rolls fold the lid curl and can flange into a double seam. The seal traps the carbonation inside the can. Pringles are manufactured as a formed potato and starch dough that is rolled into a thin sheet, stamped into a precise saddle shape, cooked to low moisture for crispness, seasoned, then stacked and packed so every crisp fits the same tube geometry. The entire process is built around the final stack because the product must be dimensionally consistent to nest cleanly. That means thickness, curvature, and shrink must be controlled more tightly than in sliced chips. The line, therefore, treats dough rheology and forming temperature as primary controls, not just cooking time. The last operation before packaging is stacking. After cooking and seasoning, the crisps move into orienting channels that flip them into a single consistent face direction. Orienters rely on the saddle shape to guide each crisp into the correct orientation. Pieces that are too flat, too curled, or warped will not travel correctly and will jam. For that reason, dimensional inspection and curvature control are enforced upstream. Once oriented, crisps enter a stacker that nests them into a column. Stack height is counted or measured by length sensors, so each tube receives a consistent number or mass. The stack is pushed into a tube, and the tube is sealed with a cap and foil or membrane, depending on the packaging design. Packaging is not passive. The tube protects the product from breakage and also provides a controlled headspace environment. The tube seal must be tight because moisture uptake softens the crisp. Barrier materials and sealing parameters are chosen to keep water vapor transmission low. Seasoning is applied immediately after cooking, while the surface still carries enough oil to act as an adhesive. Crisps pass through a rotating drum where fine seasoning powder is dosed by mass flow. Drum speed is tuned so crisps tumble without snapping. Because Pringles are uniform, seasoning distribution can be very consistent if the oil film and residence time are stable. Excess seasoning is controlled because too much loose powder collects at the bottom of the tube and affects consumer perception. Cooking creates both crispness and a stable shape. Unlike sliced chips that float in oil, Pringles are often fried on a conveyor or baked then fried depending on the process variant. The key requirement is that moisture is reduced to a low end point while the crisp is held in its saddle form. If the shape is not held, the sheet will shrink unpredictably and curl. Crisps are carried through hot oil on a belt or between forming elements that maintain curvature. Oil temperature is held tightly because it controls how quickly water leaves and how the surface sets. If oil is too cool, the crisp stays longer, absorbs more oil, and can become heavy. If oil is too hot, the surface sets before the interior dries evenly, leading to blistering or brittle weak spots. Residence time is synchronized with line speed and thickness, so the final moisture endpoint is reached consistently. Oil management remains critical. Crumbs and fines are filtered out because they burn and darken oil, changing heat transfer and flavor. Oil circulation keeps temperature uniform across the fryer width. Consistent oil quality helps maintain consistent color and prevents off notes. After frying, excess surface oil is removed with drains and air knives, so the seasoning step begins with a controlled oil film rather than variable pooling. Before frying, the product is formed mechanically from a dough sheet. The sheet is created from a blended dry base and a controlled water addition. The dry base typically includes potato flakes, potato granules, and starches that set structure. Flour or other binders can be included to tune elasticity. Dry ingredients are screened to remove lumps because lumps create weak spots that tear during sheeting and show as holes in the crisp. Water and any minor liquid ingredients are metered into a mixer where the dry base hydrates and becomes a cohesive dough. Mixing intensity is controlled because too much work develops elasticity that causes snapback and warping when stamped. Too little work leaves dry pockets that crumble and tear. The dough must be plastic enough to roll into a thin sheet without cracking, but not sticky enough to smear on rollers. Dough temperature is controlled because it drives viscosity. Warmer dough becomes softer and can stick to rollers. Colder dough becomes stiff and cracks at the sheet edges. The line aims for a narrow temperature band and uses jacketed mixers or conditioned rooms to keep that band stable. Resting time can be used after mixing to allow moisture to distribute evenly, which improves sheet uniformity. Sheeting is done through roller mills that progressively reduce thickness. The dough passes through a series of gaps rather than one large reduction. This prevents tearing and keeps thickness uniform across the width. Gauge rollers at the end set the final sheet thickness. Thickness control is one of the most important variables because thickness determines final crisp strength and how it nests in a stack. Even small thickness differences change curvature behavior during forming and change cook time in the fryer. The sheet then enters a stamping and forming section. A cutter punches oval blanks from the sheet. Scrap around the ovals is collected and returned to the dough system at controlled ratios. Rework ratio is controlled because repeated rolling changes hydration and can increase fines, affecting dough behavior. The oval blanks are transferred immediately into forming molds that create the saddle geometry. Forming molds are paired surfaces that press the blank into a curved shape. The blank is held in this geometry as it enters the cooking stage or a pre-dry stage. Holding shape during early heating is critical because shrink begins as moisture moves and starch sets. If the blank is not constrained, it shrinks unevenly and warps. Many lines use a pre-dry or bake step before frying. A brief bake removes some moisture and sets the surface so the blank can move into oil with less deformation. Baking also reduces the time in oil, which can help control oil pickup. The bake profile is tuned so it stiffens the shape without fully drying the piece. the piece must still be pliable enough to conform to the mold and avoid cracking. When the molded pieces enter the fryer, they are supported so they do not float and lose curvature. Belts and mold carriers maintain spacing and prevent contact between pieces. As moisture leaves, the structure becomes rigid. The exit condition is a crisp that is dry enough to snap, uniform enough to stack, and strong enough to survive handling. After frying, the pieces are cooled briefly to stabilize the structure before seasoning. Cooling also reduces surface volatility and helps the oil film set. Pieces then enter the seasoning drum. The drum uses gentle tumbling to distribute powder. Seasoning rate is synchronized with product throughput, and drum residence time ensures coverage without overhandling. Following seasoning, pieces are inspected and sorted. Vision systems can detect warped or broken pieces that would jam stackers. Out-of-shape pieces are rejected. This sorting step is important because stacking systems require consistent geometry to nest smoothly. Even a small number of warped pieces can create stack misalignment and tube filling issues. The oriented pieces then enter the stacker. Orientation channels guide each crisp into the same direction. The stacker nests pieces into a column and transfers the column into a tube. Tube filling is synchronized so stacks do not collide and break. Once in the tube, the product is protected from crushing and from moisture ingress. The tube is sealed, coated, and then cased. Doritos are manufactured by turning corn into a cooked masa, converting that masa into thin sheets, cutting the sheets into triangles, frying to a controlled moisture endpoint, then applying seasoning through an oil film so each chip carries a dense, uniform flavor layer without clumping. The process is anchored around seasoning adhesion because Doritos carry far more powder per unit surface than plain chips. That means the chip must leave the fryer with the right surface oil level and the right dryness. Too much oil creates heavy seasoning pockets and greasy mouthfeel. Too little oil produces bald spots and uneven flavor. The factory therefore tunes frying, de-oiling, and seasoning drum conditions as a single linked system rather than independent steps. After frying, there are chips pass through drains and controlled agitation that remove free oil while leaving a thin adhesive film. Vibration and mesh conveyors let oil fall away. Air knives can strip surface oil selectively. The target is a consistent oil film thickness that supports seasoning pickup. From there, the chips enter a seasoning drum where powder is dosed by mass flow. Drum rotation rolls the chips so both sides see powder. The powder blend includes fine salt, acids, dairy solids, spices, and flavor compounds, and it must remain free-flowing to distribute evenly. The drum residence time is long enough for coverage, but short enough to avoid breaking chips into fines. Excess powder is minimized because loose powder settles in bags and contaminates seals. Packaging begins right after seasoning. Chips feed into multi-head weighers that portion weights by combining multiple hopper dumps. Gentle drop paths reduce breakage. Bags are formed from barrier films and are often nitrogen flushed to displace oxygen and create headspace that cushions chips. Seals are made with controlled heat and dwell so the bag closes without leaks. Moisture and oxygen barriers protect crispness and flavor stability over time. All of that downstream performance depends on how the chip was built upstream. Doritos start as corn that is converted into a dough called masa. The primary transformation is cooking corn kernels in an alkaline process. Whole corn is cooked in water containing a controlled amount of alkali. This step changes the kernel structure and helps loosen the hull. It also alters protein and starch behavior so the later dough forms correctly. Cook time and temperature are controlled because overcooking produces a sticky dough that sheets poorly. Undercooking produces a grainy dough that cracks. After cooking, the corn is steeped to complete hydration. Steeping time is controlled, so water penetrates the kernel uniformly. The cooked kernels then go through washing to remove loosened whole material and to adjust surface chemistry. Wash intensity is controlled because too much washing can strip solids and change dough behavior. The washed kernels are then ground into masa using stone mills or modern grinders that produce a uniform particle size distribution. Grinding is tuned for sheetability and bite. If the grind is too coarse, the sheet will have weak points and tear during cutting and frying. If too fine, the dough becomes overly cohesive and can shrink unevenly. Water is added during grinding or immediately after to reach a target dough moisture. Moisture is the key variable that determines how easily the masa sheet forms and how it fries. The dough must be plastic enough to roll without cracking, but not so wet that it sticks to rollers and creates thickness variation. Masa mixing follows grinding. Mixing distributes moisture and stabilizes the dough. Resting can be used to let moisture equilibrate, which improves sheet uniformity. Dough temperature is also controlled because warm dough becomes sticky and cold dough cracks at edges. The system uses jacketed equipment or controlled ambient conditions to keep dough in a narrow temperature band. Sheeting converts masa into a continuous thin band. The dough passes through multiple roller gaps that gradually reduce thickness. Gradual reduction prevents tearing and keeps thickness uniform. The final gauge gap sets chip thickness. Thickness drives frying time and final crunch. It also drives how much seasoning can be carried, because thicker chips have more structure and surface roughness. The sheet then enters cutting. Rotary cutters punch triangles at high speed. Cutter timing and alignment define triangle shape and minimize scrap. Scrap sheet around triangles is collected and reintroduced into the dough stream in controlled ratios. Rework ratios are limited because repeated rolling changes, hydration, and particle damage, which can increase fines and change sheet strength. Before frying, the triangles are conditioned. Some lines use an oven or pre-dryer to remove a portion of moisture and set surface structure. Pre-drying stabilizes shape and reduces time in oil, which can reduce oil pickup. The pre-dry profile is tuned so the triangle becomes firm enough to handle but still flexible enough not to crack. Frying is the main crispness forming step. Triangles enter hot oil and immediately release steam as surface water flashes. The steam creates pores and drives moisture out. As moisture drops, the structure rigidifies and the chip becomes brittle. Oil temperature is held tightly because it controls the rate of water removal and the degree of browning. Too cool yields oily, flexible chips and inconsistent seasoning adhesion. Too hot yields fragile chips that darken and break. Residence time is controlled by conveyor speed and chip bed depth. Bed depth must be shallow, so every chip sees similar oil contact and heat transfer. Oil circulation maintains uniform temperature across the fryer width and prevents cold spots. Filtration removes fines and crumbs that burn and darken the oil. Oil turnover keeps oil quality stable, so flavor and color remain consistent. After frying, chips pass through a color sorting system on many lines. Optical sensors detect overly dark chips or defective shapes and eject them. Sorting tightens visual consistency in the bag and removes chips that would taste more bitter from heavier browning. The fried chips then go through the de-oiling steps that were set up to support seasoning pickup. The factory treats de-oiling and seasoning as a coupled system. If the seasoning formula changes, the target oil film may change too. Fine powders require less oil to adhere evenly. Larger particle blends may need slightly more oil. The line adjusts drain time, vibration intensity, and air knife settings to land at the correct film. Seasoning powder handling is its own process because Doritos powders are complex blends that must remain free-flowing. Powders are blended in large mixers and screened to break clumps. Moisture control is critical because humidity causes caking. Feeders meter seasoning into the drum at a rate proportional to chip mass flow. The drum is designed to provide enough tumbling for even coating without creating breakage. Interior lifters lift chips and let them fall through a powder cloud, promoting coverage on both sides and edges. After seasoning, the chips are screened lightly to remove loose fines. This reduces dust in the bag and helps maintain seal integrity. Then the chips are weighed and bagged, flushed with gas, and sealed. Case packing stacks bags in a way that reduces crushing forces and keeps headspace intact, because the headspace acts as a cushion. Walker-style crisps are manufactured by engineering a thin potato slice into a dry, brittle matrix with a controlled surface oil film, then locking that texture in with fast packaging that blocks moisture and oxygen. The process is easiest to follow from the fryer exit because the fryer decides the final crunch and the exact oil level that seasoning needs in order to stick. As slices leave hot oil, they are still losing steam through their pores. If they are held too long without draining, oil can continue to migrate into those pores as internal pressure drops. The line therefore moves crisps immediately onto draining conveyors and vibration decks. Vibration shakes off free surface oil, while the crisp is still rigid enough to tolerate movement. Air knives can strip oil from curled edges and from the center dish area. The objective is not a completely dry surface. It is a consistent, thin oil film that supports seasoning and gives the correct mouthfeel. Seasoning is applied while that oil film is still warm and mobile. Crisps enter a rotating drum where seasoning powder is metered by mass flow to match crisp throughput. Drum internals lift and cascade crisps so powder distributes across faces and edges. Drum speed is tuned to roll crisps without grinding them into fines. Too much agitation creates dust that collects in bags and contaminates seals. Too little agitation yields patchy coverage. For lightly salted crisps, the dosing rate is low and distribution must be especially uniform because any local salt cluster is obvious. For flavored crisps, the powder mix is more complex and often includes fine salt, acids, dairy solids, spices, and flavor carriers that need controlled humidity to remain free-flowing. After seasoning, crisps are screened to remove small fragments and fines created in slicing and frying. Removing fines improves bag appearance and reduces dust that can weaken seals. It also helps keep seasoning distribution predictable because fines carry disproportionate seasoning. Packaging is designed to preserve the crisp matrix that was created in the fryer. Multi-head weighers portion weights by combining multiple small hopper dumps. Drop paths are designed to reduce breakage. Bags are formed from barrier film and typically flushed with nitrogen to displace oxygen and create a cushioning headspace. The nitrogen headspace reduces oxidation and protects crisps from crushing. Heat seals close the bag. Seal temperature and dwell time are tuned so seals hold without wrinkles that would leak. Even small leaks allow moisture ingress, which softens crisps by raising water activity and plasticizing the starch matrix. The fryer performance that makes all of this work depends on what happened to the potato slice before it reached oil. Slices must enter the fryer separated with low surface starch and with minimal free water. If slices stick together, they cook unevenly and trap moisture. If surface starch remains, it forms a sticky film that encourages clumping and creates dark specks in oil. If surface water remains, it cools the oil locally and increases oil breakdown. That is why the pre-fry section is built around starch and water removal. Immediately after slicing, the slices fall into a flume or wash system that keeps them suspended and separated. Water flow and turbulence are tuned to strip off loose starch without tearing thin slices. Countercurrent wash systems can be used so cleaner water contacts cleaner slices near the exit. This reduces total water use while maintaining starch removal efficiency. After washing, slices are dewatered on vibrating screens and then passed under air knives. Dewatering is more important than it looks. A few extra grams of water per kilogram of slices can pull fryer temperature down and create a soft, oily crisp. Dewatering also reduces splatter and helps oil stay stable. The line targets a consistent surface dryness before the slices reach oil. Slicing itself is the origin of thickness consistency, and thickness consistency is the origin of uniform cook. Potatoes are fed into high-speed slicers, where rotating blades cut slices to a fixed thickness. Blade sharpness is critical. Sharp blades cut cleanly and preserve cell structure. Dull blades tear cells and create ragged edges that absorb more oil and generate more fragments. Blade condition is monitored by slice quality indicators like feathered edges and by mechanical signals like vibration and motor load. Blades are changed on schedule, so thickness and edge quality remain stable. Potato feed to the slicer is stabilized because potato size affects how the slicer loads and how slices land in the wash flume. Potatoes arrive in bulk and are graded by size. Oversized potatoes can overload slicer throats and cause thickness variation. Undersized potatoes produce small slices that fry faster and darken. Grading routes different sizes to different slicer lanes or to different product streams. The goal is to keep each slicer running within its preferred diameter range. Before slicing, potatoes are washed and often peeled depending on the crisp style. Spray washers remove soil and grit that would dull blades and darken oil. Peeling can be abrasive or steam-based. Abrasive peeling removes skin by rubbing against rough surfaces. Steam peeling loosens skin rapidly, which is then removed mechanically. Peeling choice affects yield and appearance. A peeled crisp tends to have a uniform, pale base color, while skin-on crisps show darker flecks and require tighter sorting later. Potato chemistry control is a major lever for color consistency. Reducing sugar levels in potatoes affect browning rate during frying. High reducing sugars lead to dark crisps at normal fry conditions. Plants manage this through raw material selection, blending of lots, and controlled storage temperature. Potatoes stored too cold can accumulate sugars and brown more. Potatoes stored too warm can sprout and lose solids. The plant aims for a consistent solids content and sugar level so the fryer can run at stable time and temperature. Once slices enter the fryer, the process becomes heat transfer and mass transfer. Moisture leaves the slice as steam. As water leaves, pores form. Oil replaces some of that volume as the slice cools and internal pressure drops. The factory manages oil uptake by controlling temperature, residence time, and slice thickness. Higher temperature drives faster moisture loss and can reduce total oil uptake, but it can also increase browning and fragility. Lower temperature increases residence time and oil uptake. The line balances these to hit a target oil content and color. Fryers are designed for uniformity. Oil is circulated and heated, so temperature is consistent across the belt width. Baffles guide flow to eliminate cold zones. Slice bed depth is controlled so slices are not stacked. Stacked slices insulate each other and cook unevenly. Many systems use in-feed spreaders that distribute slices into a single layer at fryer entry. Oil quality is maintained continuously. Filtration systems remove crumbs and starch fragments because they burn and darken the oil, creating off flavors and color specks. Oil turnover adds fresh oil and removes degraded oil fractions. Consistent oil quality gives consistent heat transfer and consistent browning. It also helps maintain a clean flavor profile. Color sorting is often used after frying. Optical systems detect overly dark crisps and eject them with air jets. Sorting helps manage natural raw material variation and keeps the bag consistent. It is especially useful when potatoes vary slightly in sugar content even after selection. Honey production begins when sealed honeycomb frames enter an uncapping machine and the thin wax layer over each cell is sliced away. The comb is already filled with thick honey, but the honey is trapped inside thousands of small hexagonal cells. Each cell is closed with a pale wax cap. Before extraction can begin, these caps must be removed without crushing the comb structure beneath them. The frames move between heated blades, vibrating knives, or rotating uncapping rollers. The wax surface breaks open in long strips. The exposed cells glisten as honey appears across the comb face. Cut wax falls away into a collection trough, carrying small amounts of honey with it. The uncapped frames then move into an extractor. This machine uses centrifugal force. Frames are loaded into a rotating basket or drum. When the drum spins, honey is flung from the open cells toward the outer wall of the extractor. At first, the honey leaves the comb in thick threads. As rotation increases, the streams become faster and heavier. The honey strikes the extractor wall and runs downward into a collection sump. The comb remains inside the frame, emptied but still shaped. The extractor speed is controlled. If it spins too slowly, too much honey remains in the cells. If it spins too aggressively, the wax comb can tear apart. The machine gradually increases speed, so honey leaves cleanly while the comb structure stays intact. The raw extracted honey flows from the base of the extractor into a coarse straining system. This first separation removes larger wax pieces, broken comb fragments, and other visible solids. The honey passes through screens, while heavier wax particles are held back. The uncapping wax collected earlier follows its own recovery path. Wax and honey move into a heated draining tank or wax separator. Gentle warmth softens the mixture and allows honey to drain away from the wax. The recovered honey joins the main stream after straining, while the wax is separated from the liquid process. The strained honey is still not ready for bottling. It contains tiny air bubbles, fine wax particles, and natural suspended material. It moves into a settling tank, usually a tall stainless steel vessel with a conical or sloped bottom. Inside the tank, time and gravity begin sorting the honey. Air bubbles rise slowly because honey is dense and viscous. Fine wax particles float upward. Heavier particles settle downward. The clearer honey remains in the middle zone of the tank. The settling tank may be gently warmed. Heat lowers viscosity, helping bubbles rise and making the honey easier to pump. The temperature is controlled carefully. The goal is not to cook the honey. The goal is to make it flow smoothly through pipes, filters, and filling valves. After settling, honey is drawn from an outlet positioned above the bottom sediment layer and below the floating foam layer. This avoids pulling in either settled material or surface scum. The stream moves toward finer filtration. Filtration can use mesh screens, cloth filters, or cartridge systems, depending on the desired clarity. The honey moves slowly because of its thickness. Pumps push it under controlled pressure through filter media that catch tiny wax particles and fine solids. The filter must be matched to the product style. A very fine filter produces clearer honey. A coarser filter leaves more natural material in the liquid. In either case, the process is designed to create a smooth, clean honey stream that can pass through filling equipment without clogging. The filtered honey enters a holding tank. This tank acts as a buffer between extraction and packaging. It keeps a stable supply ready for the filling line. The tank may include a slow agitator that turns gently, preventing temperature layers without whipping air into the honey. Honey from different extraction batches may be blended to create a consistent color, moisture level, and flavor profile. Blending is done inside large tanks. One batch may be darker and stronger. Another may be lighter and milder. Metered additions allow the final tank to reach the target specification. The blending motion is slow because honey traps air easily. A fast agitator would create bubbles that take a long time to escape. The paddles move gradually, folding the honey through itself in thick, slow currents. Moisture control is important in honey processing. Honey with too much moisture can become unstable. In a factory setting, moisture is checked before filling. If the honey needs adjustment, it may pass through controlled warming and evaporation equipment designed to reduce excess water without burning or darkening the product. The honey now moves toward the filling line. It is still warm enough to flow, but thick enough to hold its dense texture. Jacketed pipes may maintain temperature, so the honey does not cool and slow inside the line. Containers are prepared separately. Glass jars, plastic squeeze bottles, or rigid plastic tubs arrive empty and are fed into the packaging system. They move through unscramblers or depalletizers that organize them into single-file rows. Plastic squeeze bottles may be blow molded in a separate operation before arriving at the filling line. In that process, plastic is formed into bottles with flexible walls and precise neck finishes. The bottle must be strong enough to stand upright, but soft enough for squeezing. Before filling, containers pass through cleaning or air rinsing equipment. Each container is inverted or positioned under a nozzle. Filtered air removes dust or loose particles from the interior. The container returns upright and enters the filler. The honey filler is designed for viscous liquid. It does not behave like a water filler. Honey stretches, clings, and forms threads when the nozzle stops. The machine must dose accurately while preventing drips across the container rim. Piston fillers, gear pumps, or servo-controlled volumetric fillers are common for thick products. A measured volume of honey is drawn into a chamber, then pushed through a nozzle into the container. The nozzle may lower close to the bottom at the start of filling and rise as the honey level increases. This bottom-up filling reduces trapped air. Honey flows into the container as a thick amber column, spreading slowly outward. The level rises with a glossy surface. When the target amount is reached, the valve closes. A cutoff mechanism prevents trailing strings of honey. Some nozzles use suck-back action, briefly pulling product upward to stop dripping. This keeps the jar rim clean for sealing. Filled containers move immediately toward capping. Caps are fed from a hopper into a sorting bowl. The sorter orients each cap correctly and sends it down a chute toward the capping heads. For glass jars, metal or plastic lids are placed onto the threads and tightened to a controlled torque. For squeeze bottles, flip-top caps or dispensing closures are applied and tightened. The closure must seal the container without damaging the neck or deforming the cap. Some honey jars receive an induction seal or liner under the cap. In that route, a foil-lined closure passes under an induction sealing head. Electromagnetic energy heats the foil layer and bonds it to the container mouth. The cap remains above it as the outer closure. After capping, the containers pass through inspection. Fill level sensors or check weighers verify the amount of honey. Vision systems inspect cap presence, cap angle, container shape, and visible contamination. Any package outside tolerance is rejected automatically. The exterior of the container may pass through a cleaning station if any residue is detected. Light rinsing, wiping, or air cleaning removes stickiness from the outside surface. Clean containers travel more reliably through labeling equipment. Labeling depends on package shape. Round jars pass through wraparound labelers. A pressure-sensitive label peels from a backing web and attaches to the glass or plastic surface. Rollers spin the jar and press the label smoothly around the curve. Squeeze bottles may receive front and back labels. The bottle is held between belts, while label heads apply each panel. Rollers press the labels flat against the curved or slightly flexible bottle surface. Alignment guides keep the label centered. A coding system marks each package with production data. Inkjet or laser equipment applies a code to the cap, label, jar shoulder, or bottle base. The mark appears as the container moves along the conveyor. For some honey formats, tamper bands are applied around the lid and neck. A sleeve of plastic drops over the closure area. The container moves through a heat tunnel, where hot air shrinks the band tightly around the cap and neck. The band conforms to the package shape as it cools. Cherry Coca-Cola production begins when a cherry flavor stream is metered into a dark cola syrup base. The cherry component is powerful, so it enters through a controlled dosing line rather than as a large volume. A metering pump pushes it into a stainless steel tank where the cola syrup is already circulating. The agitator pulls the liquid inward, drives it downward, and folds the cherry stream through the dense syrup until the added flavor no longer exists as a separate layer. The cola syrup itself has been built before this point. Treated water enters a syrup tank first. It is not ordinary untreated water. It has already moved through filtration systems that remove suspended particles, activated carbon beds that reduce unwanted taste and odor, and polishing stages that stabilize clarity and mineral profile. A measured volume of this treated water is held inside the syrup vessel. Sweetener is added through a dosing system. In some plants, the sweetener enters as granulated sugar. In others, a liquid sweetener stream is used. The agitator keeps the water moving so the sweetener disperses quickly. If dry sugar is used, the crystals fall into the moving water and dissolve gradually. The liquid becomes heavier and glossier as the sugar disappears. Mild heat may help the dissolution process, but the syrup is not boiled. The purpose is to create a smooth, sweet base with no grit or undissolved particles. The sweet base passes through fine filtration. This removes any remaining solid material before flavor concentrate is added. Clean syrup protects the pumps, meters, proportioning valves, and filling heads later in the line. Cola concentrate then enters through a closed pipe. It brings the core cola flavor, caramel color, acidity structure, and formula components that define the base beverage. The syrup darkens almost instantly. The tank changes from a clear sweet solution into a deep brown concentrate. The agitator continues turning. Dark streaks vanish into the syrup. The mixture becomes uniform from the top surface to the outlet at the bottom of the tank. This syrup is still too strong to drink. It is a concentrated flavor and sweetener base designed for precise dilution later. The cherry flavor addition is integrated into this cola syrup system. It must not overpower the cola base or remain uneven in the batch. The mixing sequence creates a combined cola cherry syrup that carries both profiles in one concentrated stream. The finished syrup moves into a holding tank. The tank may use slow agitation to keep the syrup uniform. Sensors monitor level and temperature. From here, a sanitary pump sends syrup toward the proportioning system. A separate treated water stream leaves the storage tanks and travels toward the same proportioning unit. This water bypasses the syrup tank and remains clear until it reaches the blender. Both syrup and water pass through flow meters. The proportioner is the point where concentrated syrup becomes finished strength cherry Coca-Cola. One line carries the dark cola cherry syrup. The other carries treated water. Automatic valves make continuous adjustments so the blend ratio stays fixed, even if pressure changes inside either line. Inside the mixing chamber, the syrup and water combine. The syrup thins rapidly. The color remains deep, but the viscosity drops. The beverage now has its finished sweetness, acidity, cola flavor, cherry note, and caramel brown appearance. It is still flat. The flat drink moves through a chilling system. It passes through a plate heat exchanger made from thin stainless steel plates. A cold circulating medium flows on the other side of the plates and draws heat away from the beverage. The liquid temperature drops quickly while the product remains sealed inside the system. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. It also foams less during filling. This matters because a carbonated cola must enter cans or bottles at high speed without overflowing or losing too much gas. The beverage may pass through a deaeration stage before carbonation. In a deaerator, reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing unwanted air helps the drink accept carbon dioxide more cleanly. Carbon dioxide enters through regulated gas lines. The gas is filtered and pressure controlled before reaching the carbonator. Inside the carbonator, chilled cherry Coca-Cola meets carbon dioxide under pressure. The gas dissolves into the liquid rather than escaping as bubbles. The drink now has its sparkling bite. From this point onward, it stays inside closed pressurized stainless steel pipework. A sudden pressure drop would release foam and reduce carbonation, so the finished beverage flows directly toward the filling machine. While the liquid is prepared, containers move along their own factory path. For PET bottles, the process begins with preforms. A preform is a short, thick plastic tube with a finished neck. The threads, sealing surface, and tamper band support are already molded. The body still has to be stretched into a full bottle. Preforms enter a heating oven. Infrared lamps warm the plastic body while each preform rotates. Rotation keeps the heat even around the circumference. The neck area is kept cooler so the threads do not distort. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes downward through the center, pulling the softened plastic lengthwise. Compressed air then expands the plastic outward until it touches the chilled mold wall. The bottle shape appears instantly. The base forms into pressure-supporting feet. The shoulders and label panel set into the plastic. The mold opens and the new bottle exits by its neck ring. The bottles move through air conveyors. They are light before filling, so streams of air push them forward while rails support them by the neck. They travel toward rinsing in single-file rows. At the rinser, each bottle is gripped, inverted, and cleaned internally with filtered air or treated rinse water. It drains briefly, turns upright again, and moves toward the filler. Aluminum cans follow another route. They arrive already formed and printed, open at the top. The cans enter an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottles arrive fully formed. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and inside surface. Defective bottles are removed before they can reach the beverage. The carbonated cherry Coca-Cola reaches the rotary filler under pressure. The filler contains many valves arranged around a circular carousel. Containers enter through a star wheel that spaces them evenly beneath those valves. A bottle seals against its filling valve. Pressure inside the bottle is balanced with the filler before liquid enters. This prevents the carbonated drink from surging into foam. For cans, the filling system also controls flow carefully to limit turbulence. The valve opens. Dark, sparkling cherry Coca-Cola flows into the container in a smooth stream. In a clear bottle, the liquid rises from the base, carrying fine bubbles through the brown body of the drink. The fill level reaches the programmed height and the valve closes. The filled container moves immediately toward closure. Plastic bottles pass under capping heads. Caps are fed from a bulk hopper, sorted into the correct orientation, and delivered down a chute. Each capping head places a cap on the bottleneck and tightens it to a set torque. The tamper band locks below the neck ring. Cans move into a seamer. A thin aluminum lid is placed on each filled can. The can and lid rotate together while seaming rolls fold the lid curl and can flange into a tight double seam. The seal traps carbonation inside without glue. Glass bottles receive crown caps. A metal crown is positioned over the mouth and pressed down. The ridged skirt crimps under the glass bead, forming a gas-tight closure. Sealed containers move directly through inspection. Fill level sensors check the amount of liquid. Cameras inspect cap angle, tamper band position, lid seam, crown placement, bottle shape, and printed surfaces. Any container outside tolerance is rejected by an airjet or mechanical pusher. Bottles then move toward labeling. For roll-fed labels, printed film unwinds from a reel. Registration sensors locate the printed marks. A cutter separates each label, adhesive attaches the leading edge, and the bottle rotates as the film wraps around the body. The trailing edge is secured with another adhesive point. Rollers smooth the label around the bottle so it sits straight and tight. Cherry Coca-Cola labels identify the variant, while the liquid inside remains the same dark cola color. Shrink sleeve labels may use a different route. A printed sleeve drops loosely around the bottle. Heat then shrinks the sleeve tightly to the container contours. Glass bottles can receive glued paper labels pressed flat by brushes as the bottle turns. Cans usually carry their printed design before filling, so they move from seaming and inspection directly toward coating and packing. Ben & Jerry's ice cream mix enters the freezer barrel as a smooth liquid, then leaves as a thick, semi-frozen stream ready to catch chunks, swirls, and ribbons. The liquid mix is cold before it reaches the freezer. It has already been blended, pasteurized, homogenized, aged, and balanced for fat, sugar, milk solids, and stabilizers. At this point, it looks like heavy cream with dissolved sweetness and flavor. Inside the freezer barrel, rotating scraper blades drag across a chilled metal wall. A thin film of ice cream freezes against that wall almost instantly. The blades scrape it away before it becomes a solid sheet. The scraped crystals mix back into the liquid. More liquid touches the cold surface. More crystals form. The cycle repeats rapidly, building a creamy frozen structure instead of a hard block of ice. Air is added at the same time in controlled amounts. The air is broken into tiny bubbles and distributed through the mix. The liquid thickens as it transforms into soft ice cream. The freezer does not finish the product completely. It produces ice cream that is cold, dense, and pumpable. It must still be soft enough to accept cookie dough, brownies, chocolate pieces, nuts, caramel, fudge, fruit preparations, or other inclusions without breaking the machinery or crushing the pieces. Before this freezing step, the dairy base is built in stainless steel tanks. Cream, milk, skim milk solids, sugar, liquid sweeteners, stabilizers, and emulsifying ingredients are measured into the batch system. The ingredients enter by weight or flow rate. The tank agitator keeps the mixture moving so powders hydrate and liquids disperse. The dairy fat is one of the main structural elements. It gives richness and helps the frozen mix hold air. Sugar lowers the freezing point, so the final ice cream does not become rock hard at freezer temperatures. Milk solids add body. Stabilizers help control ice crystal growth and improve texture after hardening. Dry ingredients are added carefully. Sugar flows easily, but stabilizers can clump if they hit the liquid too quickly. A powder induction system pulls dry materials into a fast-moving stream of liquid, dispersing them before they form lumps. The tank gradually becomes uniform. Flavor bases may be added to the liquid mix at this stage. Vanilla, chocolate, coffee, fruit bases, or other liquid ingredients can be blended into the dairy stream. Cocoa ingredients require strong mixing because cocoa powder resists wetting and can form dark clumps if not dispersed properly. Chocolate mixes become darker and thicker as the cocoa hydrates. The blended mix is pumped through filters to remove undissolved particles before heat treatment. It then moves through a pasteurization system. In a continuous plate heat exchanger, the mix flows between thin stainless steel plates while hot water or steam-heated fluid moves on the other side. Heat transfers quickly through the metal, raising the mix temperature under controlled conditions. The hot mix passes through a holding tube for the required time. The flow rate and tube length control the exposure. After holding, the mix enters the cooling side of the exchanger, but first, it may pass through a homogenizer. Homogenization forces the hot mix through very small gaps under high pressure. The fat droplets are broken into smaller droplets and spread evenly through the liquid. This creates a smoother mix and improves body. Without this stage, fat could separate or create uneven texture in the finished ice cream. After homogenization, the mix is cooled quickly. Cold fluid on the opposite side of the heat exchanger pulls heat away. The mix exits cold and moves into aging tanks. These tanks hold it at low temperature for several hours. Slow agitators keep the mix uniform without whipping in air. During aging, fat crystallizes into a stable form. Stabilizers fully hydrate. The liquid becomes slightly thicker. This step prepares the mix for freezing. Aged mix whips better, freezes more smoothly, and carries inclusions more evenly. Inclusion preparation happens separately from the dairy mix. Cookie dough pieces are formed from dough, cut into small chunks and chilled or frozen so they remain distinct inside the ice cream. Brownies are baked in sheets, cooled, cut into cubes, and frozen or chilled to hold their shape. Chocolate chunks are formed, cooled, broken, or cut to size and screened so only the correct pieces continue. Nuts are roasted or prepared, cooled, and sized. Caramel cups, fudge flakes, candy pieces, or baked inclusions are held cold so they do not smear when added. Each inclusion must be strong enough to pass through the feeder, but tender enough to bite through in the final product. Swirls are prepared in heated or chilled holding systems depending on the ingredient. Fudge swirl is cooked into a thick, glossy sauce. Caramel is blended and held at a temperature where it flows, but does not become watery. Fruit swirl contains fruit preparation, sugar, and stabilizing ingredients to keep the texture spoonable at frozen temperatures. These swirls do not enter the main mix tank. They are added after freezing, so they remain visible as ribbons rather than disappearing into the base. The timing is important. If a swirl enters too early, it blends into the ice cream and becomes a uniform color. If it enters too late, it may not distribute across the pint. The semi-frozen ice cream exits the continuous freezer and enters a fruit feeder or ingredient feeder. This machine meters solid inclusions into the moving ice cream stream. A hopper holds the chunks. An auger or pocketed rotor releases them at a controlled rate. The pieces fall into the ice cream and are folded through by the flow of the product. The feeder must avoid crushing the inclusions. Cookie dough chunks, brownie cubes, and chocolate pieces pass through wide openings and gentle mixing zones. The goal is not to grind them into crumbs. The goal is to suspend large, recognizable pieces throughout the dense, frozen base. The stream then moves toward the variegate or swirl injector. Thick sauce is pumped through dedicated lines and injected into the ice cream as it moves toward filling. The sauce enters in ribbons, streaks, or bands. It does not fully mix. It travels as separate colored paths inside the base. The product now contains frozen ice cream, air cells, ice crystals, fat structure, chunks, and swirl. It is soft enough to pump, but thick enough that pieces do not immediately sink. It reaches the pint filler through short, insulated piping. Empty Ben & Jerry's pint containers feed into the filling line. The paperboard tubs are stacked and separated one at a time. Each container is placed into a pocket or held beneath a filling nozzle. The filler must handle a product that is partly frozen and full of pieces. The nozzle deposits ice cream into the pint in a controlled pattern. It may fill from the bottom upward or use a rotating motion to distribute swirls and chunks. The product enters as a thick rope, folding into the container and building upward. Large inclusions settle into the base as the pint fills. The fill level is controlled by volume or weight. Too little product creates an underfilled pint. Too much product can interfere with lidding or create product on the rim. The filler cuts off cleanly, so the rim remains clear. Some flavors need extra topping or a core style addition. In those formats, the filler may deposit part of the ice cream, inject a central stream of caramel, fudge, cookie butter, or another component, then finish with more ice cream. The core must remain centered and thick enough to stay visible when scooped. After filling, a lid is placed on the pint. Lids feed from a magazine or hopper, separate one at a time, and press onto the rim. The container now holds soft ice cream that is shaped but not yet fully hardened. The pints pass through check weighing. The machine weighs each container and rejects any pint outside tolerance. Vision systems inspect lid placement, container condition, print orientation, and visible rim contamination. The filled pints move quickly toward hardening. This is where the soft, frozen product becomes stable enough for storage and distribution. The pints enter a hardening tunnel or spiral freezer. Very cold air moves at high speed around the containers. Heat leaves the pint from the outside inward. The ice cream firms against the container wall first. The center hardens more slowly. The air movement must be strong because pints are thick. Packages, and the product contains chunks and swirls that affect how heat transfers. Nerds begin as a hot, clear sugar melt that is deliberately forced into a brittle glass because the final candy is defined by controlled fracture rather than molding. The line starts by preparing a sugar solution that can be concentrated without seeding unwanted crystals. Granulated sugar is screened to remove clumps and to tighten the crystal size range. Fines are limited because they dissolve too fast and can caramelize at hot surfaces. Water is filtered and tempered so dissolution conditions stay repeatable. Corn syrup is held in jacketed tanks to keep viscosity stable for metering. Acid powders, salts, flavors, and colors are staged in separate feeders because nerds often run multiple flavors in parallel. Sugar and water enter a dissolver with strong agitation. The goal is a fully dissolved solution with no grain residue. Any undissolved grain becomes a nucleation site that can trigger premature crystallization. The solution passes through strainers to remove stray solids and then feeds a continuous cooker. In the cooker, the syrup is heated rapidly to drive off water and raise solids to the level needed for a hard candy glass. Many systems heat under pressure so temperature can rise above the normal boiling point without flashing. That allows fast heat transfer and short residence time. The syrup then enters a flash stage where pressure drops and water vapor leaves quickly. Flashing tightens final moisture and also cools the syrup slightly by evaporative loss. Final solids must land in a narrow window. Too wet and the sheet will bend and tear instead of shattering. Too dry and the sheet will explode into excessive dust when fractured. Corn syrup is injected as a crystallization control lever. It reduces uncontrolled graining and helps keep the candy glass consistent from run to run. Its metering is precise because it also changes brittleness and fracture behavior. After the final concentration step, the syrup is cooled through heat exchangers to a temperature that protects flavors and supports controlled casting viscosity. The process often splits into two streams at this stage to create two flavors and two colors for the paired pack format. Each stream receives its own acid and flavor additions. Acid is added after the hottest zones because high temperature and low pH accelerate sucrose inversion and can change texture. The acid is usually dosed as a solution to ensure fast dispersion. pH is controlled because it influences sourness and also influences how hygroscopic the finished candy will be. Flavors are injected late and mixed rapidly. Oil-based flavors are emulsified or carried so they will disperse evenly. Color solutions are filtered and then metered into each stream. Uniform color matters because nerds are small and translucent and any streaking is visible. Static mixers fold the flow repeatedly to eliminate bands before casting. Casting turns the hot syrup into a thin sheet that can be fractured into granules. The syrup is deposited onto a cooled steel belt or onto trays as a continuous ribbon. Deposit rate and belt speed set thickness. Thickness is a key variable because it determines cooling rate and fracture size distribution. A thicker sheet cools slower and can retain internal stress. A thinner sheet cools fast and can become too brittle at the surface. Cooling is engineered to produce an amorphous glass with minimal crystal growth. Cooling plates under the belt pull heat out evenly. Air above the sheet is controlled so humidity does not condense, and so surface remains clean. Rapid cooling locks the syrup into a glassy state. If cooling is too slow, crystals can grow and the candy becomes gritty rather than sharp and crunchy. As the sheet cools, it can be conditioned to create predictable fracture behavior. Some lines flex the sheet slightly over rollers to introduce controlled microstresses. Others lightly score the surface to create preferred break paths. The aim is to reduce random oversized chunks and reduce the need for aggressive crushing later. The sheet must reach a brittleness that breaks cleanly under compression rather than smearing. Once the sheet is brittle, it is released from the belt and fed into a primary breaker. The primary breaker uses toothed rollers or oscillating bars to crack the sheet into chips. This first break is staged to avoid shattering into dust. Chips then feed a secondary reduction stage, often roll crushers, that bring pieces down toward the final nerd size range. Roll crushers are used because they apply compressive force and yield angular fragments rather than rounded beads. Crusher gap is the main size control. A smaller gap yields more fines and a narrower top size. A larger gap yields more oversize that must be recirculated. Feed rate must be steady because surges cause inconsistent reduction and more dust. Roll speed and surface texture also matter because they control how the chip is gripped and fractured. The goal is irregular pieces with sharp facets but limited powder. After crushing, the material enters screening. Vibratory screen decks separate by size in multiple fractions. The target fraction continues as product. Oversize is returned to the crusher for another pass. Fines are removed because they clump easily and create dusty packs. Fines can be used as controlled recycle seed in some systems, but only in small ratios because they raise cohesion and reduce free flow. Because nerds often come in two distinct colors, each stream is processed separately through crushing and screening. This keeps recycle loops color pure and prevents shade drift. It also allows each stream to be tuned for its own brittleness because acid and flavor loads can shift glass strength. If one flavor tends to shatter more, the crusher gap can be opened slightly for that stream while keeping the other tighter. Conditioning follows sizing. Even though the candy is glassy, it can hold slight moisture gradients from casting and cooling. Conditioning allows moisture to equalize inside each granule. This stabilizes crunch and reduces caking risk. Conditioning bins use controlled dry air so the product does not absorb humidity. Humidity control is critical because hard candy surfaces can become tacky when water activity rises. Tack leads to clumping and also to color transfer between pieces. A light finishing step can be applied to improve flow. Anti-caking agents can be dusted at very low levels in a tumbler. The purpose is to reduce surface adhesion points and to improve hopper flow. Application must be uniform because local over-application changes mouthfeel and creates visible dust. After tumbling, the product can be aspirated lightly to remove excess loose powder. For versions that emphasize a stronger sour burst, some sourness can be placed at the surface rather than only in the body. This is done by misting a very small amount of binder and then applying an acid sugar blend. The binder must be extremely light so it does not dissolve the glass surface. The acid blend adheres, and then the product is dried quickly to set. This creates a fast sour hit at the tongue because surface acids dissolve first. If the product format requires blending the two flavors, blending is performed after each stream has been sized and conditioned. Gravimetric feeders meter each color stream into a blender at the target ratio. The blender uses gentle paddles, so it mixes without grinding. Over-mixing would generate fines by abrasion. The blending time is therefore short, and the geometry is chosen to fold the streams rather than shear them. Before packaging, the blended product is screened again to remove any fragments created in blending and conveying. This final screen improves pack cleanliness and improves weigher accuracy. Metal detection can be placed at this stage because product flow is stable and pieces are dry. Packaging begins with controlled feeding into weighers. Multi-head weighers are common because they can combine multiple small hopper dumps to reach target weight quickly. Consistent flow into the weigher depends on low fines and low humidity. Hopper walls are steep and surfaces are low friction. Vibration is used sparingly because vibration can create abrasion dust. For bag formats, the weighed portion drops into a vertical form fill seal machine. Film is formed into a tube and sealed longitudinally. The portion drops through a funnel and settles. Transverse seals close the bag above and below the portion. Seal timing must keep granules away from the seal jaws. Dust management is important because sugar dust in the seal area can weaken the seal. Oreos are manufactured by producing a cocoa cookie wafer with a controlled snap and surface texture, producing a fat-based creme that holds shape without refrigeration, then assembling two wafers around a measured cream deposit before packaging to protect crispness. The cookie wafer begins with flour and cocoa handling because particle size and moisture define dough behavior. Flour is sieved to remove lumps and to aerate it for consistent hydration. Cocoa powder is sifted because it compacts and forms clods that create dark streaks. Sugar is screened to control crystal size and reduce dust. Leavening and salt are weighed precisely because they drive spread and porosity. Fats are tempered to a plastic consistency so they cream evenly and do not separate during mixing. Water is tempered because dough temperature controls sheeting and bake spread. Mixing starts by building a fat-sugar phase that controls texture. Fat and sugar enter a mixer and are creamed until sugar. Crystals are uniformly wetted and small air cells are incorporated. Air incorporation is controlled because it influences wafer porosity and snap. Too much air yields fragile wafers that crumble during sandwiching. Too little air yields dense wafers that lack the intended crisp bite. Salt and leavening can be added during creaming so they disperse evenly through the fat phase. Water is introduced next in a controlled stream. The water level is set to produce a dough that sheets cleanly without sticking. Water also activates leavening and hydrates flour. Cocoa powder and flour enter after water, so they are hydrated evenly. Mixing energy is reduced during flour addition to limit gluten development. Excess gluten makes wafers tough and increases shrink during baking. The endpoint is a cohesive dough that is uniform in color with no dry pockets. The dough is then conditioned for forming. Conditioning allows moisture to distribute and lets the dough relax so it does not snap back after sheeting. Dough temperature is held in a narrow band. Warm dough becomes sticky and smears on rollers. Cold dough cracks and produces rough edges. The line uses controlled dwell time and jacketed hoppers to maintain stable dough temperature. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through a series of reduction rollers that gradually thin it. Multiple reduction stages prevent tearing and keep texture uniform. Gauge rollers set the final thickness tightly because thickness controls bake time and final snap. Surface flour dusting can be used sparingly to prevent sticking. Excess dusting is avoided because it burns and creates specks. The sheet enters rotary cutting and embossing. Rotary cutters punch round wafers from the sheet while an embossed pattern is pressed into the surface. The embossing is functional. It controls thickness uniformity, adds texture, and influences how creme bonds. Docking holes are also created during this step. Docking vents steam during baking and prevents blistering. The sheet scrap around the cutouts is lifted and recycled back into the dough stream under controlled ratios. Scrap ratio is limited because repeated working increases gluten and changes dough rheology. Cut wafers transfer to an oven band and enter a tunnel oven. Baking is zoned to set structure and drive moisture to a low endpoint. Early zones melt fat and allow the dough to expand slightly as leavening gases form. Starch gelatinizes and protein set, turning the dough into a porous solid. Mid-zones develop color and drive off moisture. Later zones finish drying so the wafer becomes crisp and stable. Moisture endpoint is critical. If moisture is too high, wafers soften in the package and the sandwich loses snap. If moisture is too low, wafers become brittle and crack during assembly. Oven temperature and airflow are tuned to reach a narrow moisture band. Airflow affects surface drying and color. Strong airflow dries faster and can increase snap. Lower airflow yields a gentler bake and can retain a softer bite. The line controls top and bottom heat to prevent warping and ensure even bake across the wafer. After baking, wafers exit hot and fragile. Cooling stabilizes structure as fats resolidify and moisture equilibrates. Cooling conveyors use controlled airflow. Dehumidified air is often used because crisp wafers can absorb moisture from humid air. Cooling brings wafers to a temperature suitable for creme application. Wafers that are too warm will soften the creme on contact and can cause slip. Wafers that are too cool can be brittle and prone to edge chips. Wafers are sorted and oriented for assembly. Vision systems can reject misshapen wafers and cracked wafers. Thickness checks and color checks verify the oven profile. Good wafers are aligned in lanes, so the embossed side faces the correct direction. Alignment is important because the pattern must be consistent on the outside of the sandwich. Cream. Manufacture runs as a separate stream because it is a fat-based system that must remain stable and non-gritty. The cream is built from sugar, fat, and emulsifiers plus flavor. Sugar is milled or selected to a fine particle size so the cream feels smooth. The fat base is prepared from vegetable fats that are melted and then cooled to a specific plastic state. Plastic state matters because it determines how the cream whips and how it holds shape. Cream mixing begins by blending fat and fine sugar under shear. The mixture transitions from dry and crumbly to smooth as fat coats sugar particles. Emulsifiers are added to reduce viscosity and improve spread. Flavor is added late, so it remains strong. The cream is mixed until particle wetting is complete and the texture is uniform. Air can be incorporated in a controlled way to adjust density. Higher aeration yields a lighter cream that compresses easily. Lower aeration yields a denser cream with firmer bite. Temperature control in the creme is critical. If the creme is too warm, it becomes too fluid and can squeeze out during sandwiching. If it is too cold, it becomes stiff and can crack or fail to adhere. The process holds creme in a narrow temperature range where it is depositable and retains sharp edges after deposition. Cream is delivered to the assembly line through heated or conditioned piping. The depositor meters a precise mass onto each wafer. Depositing is typically done as a spiral or star pattern. The pattern controls spread when the top wafer is applied. The deposit height determines final sandwich thickness. Weight control is tight because it affects bite and package count weight. As soon as cream is deposited, a second wafer is placed on top. Placement systems pick wafers and align them over the cream deposit. The wafers are pressed together with a controlled compression. Compression spreads the cream to the edge without breaking the wafer. Too much compression crushes wafers and causes overspread. Too little compression leaves a tall deposit and weak adhesion. Compression also sets the final wafer to creme contact, which controls stability during transport. After sandwiching, the cookies move through a short setting conveyor. During this stage, the creme fat network stabilizes and holds the sandwich geometry. Cooling can be applied to firm the cream slightly. The goal is a sandwich that can be handled and packed without creme smear. The product is then inspected. Vision checks can detect misaligned wafers and missing cream. Rejects are removed automatically. Packaging is designed to protect wafers from humidity and to protect sandwiches from breakage. Sandwich cookies are stacked into columns and placed into trays. Trays hold stacks in position and reduce movement that would chip edges. The tray is then sealed inside a moisture barrier film. Film barrier performance is critical because wafer crispness depends on low moisture pickup over time. Stacking is controlled, so columns are uniform height. Uniform columns prevent uneven pressure that can break wafers. The stacking system uses lanes and pushes that align cookies without scuffing. Crumb control is important because crumbs in seal areas can compromise seal integrity. The line uses crumb extraction near tray loading and near sealing stations. The tray and film system passes through a heat seal station where the film is sealed to the tray. Seal temperature and dwell are tuned to create a continuous seal without warping the tray. Leaks allow moisture ingress, which softens wafers. Sealed trays are coated and checked by vision. Check weighers confirm pack weight. Sealed trays are then inserted into outer cartons. Cartons are erected and loaded with trays. Cartons add stacking strength and protect the film from puncture. Cartons are closed and glued. Finished cartons are case packed and palletized. Snickers starts as 3 independent streams that only meet at the assembly belt because nougat, caramel, and chocolate each require different heat histories and different flow behavior to stay consistent at scale. The nougat stream is built around controlled aeration. Sugar and glucose syrup are metered into a cooker and concentrated to a target solids level that will support a stable foam once mixed. The cook profile is kept short because long high heat residence darkens sugars and shifts viscosity. The syrup exits the hottest zone and is conditioned to a temperature where it can strengthen a protein foam without scorching it. In parallel, a foaming phase is prepared as a protein solution that can hold fine bubbles. The solution enters a continuous aerator where airflow and shear are controlled to generate a narrow, bubble-sized distribution. Density is measured continuously because density drives bar weight and final bite. If density drifts, the bar becomes heavy and tight. If density drops too far, the nougat becomes fragile and can collapse during cutting. The hot syrup and the foam meet in a continuous mixer designed to fold rather than whip. Folding distributes syrup through the foam while preserving bubble walls. The syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be dosed in small amounts to stabilize the air-fat sugar system and to keep the nougat smooth as it cools. Once the nougat reaches specification, it is deposited as a continuous slab onto a moving belt. A spreader head lays down a uniform band, and gauge rollers set thickness. Thickness control matters because it defines the core cross-section and the later chocolate ratio. The slab enters a cooling tunnel with staged zones that remove heat gradually. Gradual cooling prevents a hard surface skin forming over a warm interior because that skin can crack when the slab is bent or cut. While nougat is being formed, a caramel stream is cooked in parallel. Caramel starts as sugar and glucose, syrup combined with dairy components. The cook concentrates the mix to a solid's endpoint that yields elasticity rather than glassiness. If solids are too low, the caramel flows and smears on knives. If solids are too high, the caramel fractures and creates sharp cracks under the chocolate coat. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it remains depositable and stable. Caramel is held in jacketed tanks with gentle agitation to prevent a surface skin. It is delivered to a depositor through heated lines that keep viscosity constant. The depositor is designed to lay down an even sheet rather than a rope. An even sheet is important because Snickers requires predictable bite across the full width of the bar. Peanuts are handled as their own stream because their size and dryness control both crunch and line stability. Roasted peanuts are screened to remove fines and broken fragments that would create dust and weak points. The nut size band is chosen to give a consistent surface coverage without tall peaks. Peaks can pierce the chocolate curtain and create thin spots. Peanuts are cooled after roasting, so residual heat does not soften caramel and does not melt chocolate during enrobing. Assembly begins when the cooled nougat slab reaches the layering station. Caramel is deposited onto the nougat as a continuous layer with a controlled thickness. A leveling bar spreads the caramel and smooths the surface. The temperature of both layers is managed closely. The nougat surface must be firm enough to support caramel without compression. The caramel must be warm enough to bond without sinking into the nougat. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the width with a calibrated feed rate. The nuts land on caramel while it is still tacky, so they adhere. A light compression stage can press nuts into the caramel to improve lock-in. Compression is tuned, so it increases contact without crushing nuts into fragments. The layered slab then enters a conditioning zone. This zone firms the caramel enough for clean cutting and locks nut position. Conditioning is staged to avoid large thermal gradients between nougat and caramel. Large gradients cause differential contraction and can create separation lines. The goal is a slab that behaves as one piece under knives. Edge trimming follows because slab edges often vary in thickness. Rotary knives remove edges and send trim to controlled rework streams. The main slab is then cut into lanes. Lane knives create long ropes of constant width. A crosscutter then cuts the lanes into bar lengths. Knife timing is synchronized with belt speed to maintain tight weight control. Knife surfaces and temperatures are managed because caramel can stick and smear if the blade is too warm or too cold. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between adjacent bars. Transfer points minimize drop height because impact can dislodge nuts and can dent the nougat. A brief pre-chill can be used to firm the bar surfaces. Firmer surfaces improve chocolate coverage and reduce nut movement during curtain contact. Chocolate coating is prepared in a separate system where temper is the critical parameter. Chocolate is melted and filtered to remove unmelted particles. It is tempered in a continuous tempering unit that heats and cools in stages. The process builds stable seed crystals and then sets a working temperature that keeps viscosity steady. Viscosity matters because it defines curtain thickness and therefore coating weight. If viscosity drifts, the bars become heavy or exposed. Enrobing applies chocolate with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a bottoming roller or a bath section that lays a uniform base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the thickness at edges and the foot at the base. Air knife settings are tuned so they remove excess without exposing nuts at corners. If a top pattern is used, a stringer drizzles thin lines across the wet surface. The pattern must be applied while the base coat is still tacky enough to bond. The bars then enter the cooling tunnel immediately, so the coat sets without slumping. Cooling is staged to protect chocolate crystal structure and to prevent cracks around nut peaks. The first zone sets the surface quickly, so the coat holds shape and locks nuts in place. Subsequent zones cool more gradually, so stable crystals grow without stress. Tunnel humidity is controlled to prevent condensation because condensation can create bloom and surface haze. Bars exit at a temperature that supports wrapping without scuffing. During cooling, the internal layers also stabilize. Nougat firms as its fat phase crystallizes and its bubble. Walls become more rigid. Caramel reaches its final elasticity and stops flowing at the interface. The chocolate coat becomes a barrier that slows moisture exchange and protects texture. Inspection follows cooling because surface defects are easier to detect when the coat is fully set. Vision systems check for exposed edges and bald spots and heavy feet. Weight checks verify that cutter control and coating control are stable. Metal detection can be placed before wrapping. Defective bars are diverted to rework. Rework is managed carefully because tempered chocolate cannot be recycled directly into tempered streams without remelting and retempering. Wrapping begins with steady bar spacing into a flow wrapper. Film is formed around each bar and sealed with heat and pressure. Sealed well and temperature are tuned to create strong seals without shrinking film onto the chocolate. Film tension is controlled to prevent scuffing. Code printing is applied for traceability. Wrapped bars can be collated into multi-packs or cartons. Collation uses lanes and gating, so bars group without impact. Cartons are erected and loaded and closed. Finished units are case-packed and palletized. Case patterns reduce movement that can abrade wrappers and stress seals.